body's still adjusting. It'll take some time, but it'll get there. It has to. You know? You know what I mean? You know what I mean, Jellybean? Good morning. Good, beautiful morning, everyone. Nancy Pelosi's good morning. She says, good morning. Good morning. It's Sunday. Sunday morning. What is that say? Okay. Good, beautiful morning. Right. Good morning. Let's set ourselves up right here. Alright, let's hit on key. Forties. Okay, Valine valve, not polar hydrophobic. Psychometry of the alpha or carbon, not urine acids, glycines. Except glycine. Chiral. OL. Yeah. Proline. Proline causes kinks in the alpha helixes, breaks alpha helixes, but it also is useful in the rotation and assigned at the turns of beta sheets, useful for making the turns in the protein in the polypeptide chain. Alanine as a methyl. Non-polar. Yeah. Yeah. It says kite with a long carbon chain and NH3 plus at the end. This is lysine, LIS, K. Lysine is basic, polar, positively charged. Yeah. Phenylalanine is nonpolar. Phenylalanine nonpolar, FEF, nonpolar. Adds the guanidinium group at the end. Oh shoot, not phenylalanine. No, that's arginine. No, phenylalanine is polar. Oops, I mean nonpolar. Yeah, that's what I wrote there. Nonpolar. Absorbs UV light. Absorbs UV light. Glycine, achiral, gly, G, nonpolar. Isoleucine, right as early at the beta carbon. It's a little kind of check mark. Isobutyl. Oh, secbutyl. Yeah. Or tryptophan. Tryptophan has the double cyclic ring structure. Tryptophan. tryptophan W. Yeah, maybe it says there. Just W. Okay, nonpolar aromatic. Nonpolar aromatic. Emits fluorescent light. Oh. Tryptophan emits fluorescent light. Phenylalanine F, nonpolar. Phenylalanine nonpolar is the benzyl group. Benzyl group absorbs UV light. Just so. An amino group and a carboxyl group. Methionine, meth. The smelly caterpillar goes to ladder, climbs twice, passes sulfur gas, and puts a methyl cap on it. Boom, 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 boom. Hydrophobic. Yeah, yeah, hydrophobic, nonpolar. Contains a thiol group. Glycine, nonpolar, achiral. Yeah. Serine sips a carbon. Serine sips a carbon chain. Wait, serine sips straw with a hydroxyl tip. So hydroxyl tip, polar, uncharged. Yeah, neutral. This is glutamine, glutamine GLN, one letter Q, side chain polar. Yeah. This is alanine, ALA, A, nonpolar, hydrophobic. Stereochemistry is L relative configuration, except for cysteine, which has R, and the other ones are S. There's a YouTube link on this. Alright, sure, go watch this as well. There was another one yesterday that I wanted to watch. Yeah, I still like Point. We'll have to watch today. Okay. Um, 309 is a tree that branches has a methyl and an OH group. Has a methyl and an OH group, polar and charged. Methyl and an OH group. Yeah. Tree fork, tree fork, tree fork. Zwitter ion. Tyrosine, TYR, Y, aromatic, polar. Precursors to catecholamines. Catecholamines. Proline. Yeah, breaks the alpha helixes. Breaks the alpha helixes. Binds to itself. Useful in the turns and rotations in beta plated sheets. Inflexible, rigid. Hydrophobic. Tyrosine is like phenylalanine, but it has an OH group. It's not polar, rarely polar. Precursor to catecholamines. This is the guanidium group. Guanidinium group found in arginine. There's a basic side chain. It's going to be pKa2 plus pKa3 divided by 2. I think it's a symbol that I have here, which we will get into. We'll get into. And then once we do that, we'll do Anki, we'll review, and then we'll move on. Well, we'll review, and then we'll structure review, and then we'll move on. The amino acid cysteine. Cysteine likes to comb her hair with sulfur. Cysteine likes to comb her hair with sulfur. Cysteine likes to comb her hair with sulfur. Cysteine polar uncharged. SH. Yeah. Cysteine likes to comb her hair with sulfur. Oh, Cysteine's hairbrush has a sulfur handle. Cysteine's hairbrush has a sulfur handle. This is histidine with the histidine his H. Oh wait, no, that isn't it. No, it's not, isn't it? This is tryptophan, TRP, TRP, W, TRPW, tryptophan, tryptophan, TRPW, nonpolar, contains the indole group, emits fluorescent lights. Indole group, PA1 plus PA2, PKO2 divided by 2. For the N terminus, C terminus. Yeah, buddy. Asparagine is has the amide, has a neat amide group, So C double bond O H2. Polar uncharged. C double bond O NH2. Yeah. Okay. Asparagine. Shorter than glutamine. Glutamine has a longer carbon chain. PK1 plus PK2 over 2. This is the indole group found in tryptophan. Glutamine, so quinzamide, longer than asparagine. Polar uncharged, longer carbon chain by 1 carbon. Okay. This is classic proline, Pro-P, breaks alpha helixes, rigid and flexible, causes kinks and is kinky, causes breaks in alpha helixes, found at the terminus in the beta pleated sheets. Hydrophobic, and it's an amino acid. This is This is 309 treethyl forks, OH2 and a methyl. 309 THR, T polar. Tryptophan emits UV light, has the indole group. It has a 2 cyclic ring structure, the indole group. DRPW. Yeah. Emits fluorescent light. Yeah. Phenylalanine has a benzyl aromatic. It's F. Phe. PHE. Phe nonpolar. Oh, this one absorbs. Absorbs UV light. Absorbs UV light. Lysine. Lysine is a kite with a long chain, NH3 plus at the end. Lysine, polar, basic, positively charged. Hydrophilic. This is gonna be. This is gonna be. This is gonna be. Histidine. 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 HISH. I'm gonna say. Basic. Polar. Hydrophilic. Oh, histidine is neutral at physiological pH. That's definitely something I should remember. Good day to you, sir. Serine sipped a short straw with a hydroxyl tip. Serine polar hydrophilic. Uh, 309 THRT polar. A short tree with a hydroxyl methyl group. Okay. It says arginine, ARG, ARGR. This is polar, basic, positively charged. Contains the guanidinium group. Guanidinium group. Okay. Valine has a fork. A V fork. It splits. Nonpolar, hydrophobic. Credit A to that one. Arginine, ARGR, has a guanidinium group. What does that say about R? Rocket tip guanidinium. This is the amidazole. Found in histidine. Tyrosine is like phenylalanine. Tyrosine is like phenylalanine. Adds the hydroxyl, and it's polar. This is this is gonna be leucine, LEU, L, hydrophobic. That's about it, really. What do they say about leucine? A long fork. It's a long fork. Isobutyl. Histidine contains the imidazole group. SH polar. Neutral at physical pH. Imidazole. Okay. This is asparagine. ASNN. It's a neat amide. A neat short amide. Acetyl carbon NH2. Don't know what else to tell you. Polar. This is serine. Sip through a short straw with a hydroxyl tip. So here's going to be polar. Aspartate. It's D double O's. Acidic, negatively charged. Have the S absolute configuration. It's got the same length. It's a little bit different length on this one. That's good, I think. D double O, same one. Aspartate, ASP day, negatively charged, polar, cysteine, cysteine has a sulfur handle. Cysteine has a short sulfur handle. Polar, sulfur handle. Glutamate, glue, acidic, is longer than aspartate, has a longer chain, and then double polar, negatively charged. Yeah. Relative, absolute is cysteine, SYS, C, polar, CYS, yeah. Asparagine. Asparagine and has a netamide, short netamide. C double O NH2, polar neutral. That's gonna be PA2, no, PA1 plus PA3, pKa1 plus pKa3 over 2, pKa1 plus pKa3 over 2. This is indole group, indole, double cyclic ring. Found in tryptophan. Glutamine is the queen's amide. has a longer chain than asparagine, polar. Isoleucine, isoleucine, ille, I. Non-polar, hydrophobic. Boom. Ille, I. Double O's. Let's say glutamate, glutamic acid, GLUE, GLUE, acidic, negatively charged. Imidazole is just found in histidine. Histidine has physiological, close to physiological, has a pH of 6, which is close to physiological pH. Imidazole, cyclical structure within. On a double. Lysine. Okay, a kite with a really long chain, and then an extreme. At the end, polar basic. Leucine. 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 Leucine has a longer chain fork. Yeah, longer chain fork. Methionine. Methionine. Met. M. Non-polar. Hydrophobic. Has a thiol group. Ether group. Ether. Guanidinium group. Guanidinium group. Glycine. Phenylalanine. PHE. F. Hydrophobic, non-polar, and it absorbs UV light. Yeah. Okay. Arginine has the guanidinium group. Guanidinium. Yeah. Rocket with a guanidinium at the tip. Basic. Positively charged. Polar. Histidine has the imidazole group. Basic. Polar. Neutral at physiological pH. Neutral at physiological pH. Aspartate. Double O's. Negatively charged. Polar. glutamate, longer chained aspartate, bicarbon. Yeah. Imidazole group, cyclic restructure in double bonds and double bonds and H found in histidine. Indole group found in tryptophan, double cyclic restructures. Yeah. Guanidinium found in arginine. Okay, that's static. One do. What does that mean? One do. We can't do high yield for now. At least not yet. So, huh? Oh, I think. So now let's do let's write down the plan. Yeah, okay, so the plan for today will be and then we'll do IU DAG, and then let's do protein analysis techniques, and we'll do enzyme structures. Look, there's not that much here, I guess. Maybe there's. I'm not sure. I feel like we could do both of these. And then let's get to maybe enzyme kinetics. So let's protein analysis. Enzyme structure functions. Yes, sir. Got ourselves a plan. A master plan. Right. Okay. Yeah. Val will do that when it comes to structures. Okay. For now, let's read the high yield then. I'm just gonna center myself so I can read it here. Oh, wait. What is that? I guess we'll just read both. No, it's the same. Okay, that's fine. I'm not gonna worry about that right now. One thing at a time, slowly. Slowly. I said slowly. Sure. Okay, let's go back to the card. All right, so let's read this one. For now, let's because I feel like I'm still missing some stuff. I mean, I have the high yield that I felt like I needed to learn. So go ahead and find this. High yield. Let's find. I don't know where you guys can find it, but just find it. You know, just maybe type it in or something. Like this or something, and maybe it's in this one right here. So just click on this one and download it. Right. Oh. It's $80. So just get it. You know, just get it. I'm just following this program, right? Informing future doctors. So I don't know, math guide bundle. It's $80. I would get it. So just get it. All right. Anyways, let's exit out and let's click on it. It's also gonna tell us, you know, by the week, right? From this one, I think, condense the main idea. I would think it's this one. Oh no, main idea here. So this is something else. Maybe that's for later. Oh, simplifying the question set. So that's somewhere else. That's fine. Anyways, let's just go to where we're at. So we did. So we should be here. I don't know why it's like that. Maybe that's just how it is. Whatever. Anyways, let's read. Oh man, my eyes. I still have yet to do this, so we'll do this today. No, let's add a new chat then. Yeah, I want to know what this is talking about. Maybe there's an easier way to remember this. Oh, okay. I wonder if I can add a card. Can I add a card? Let's figure out how to add a card. Because I think this is pretty important. Front field. In the front field. I don't think front field and the back field. I don't think it understands. Oh, I didn't put anything. Okay. Sometime. Let's try that. First field is empty. First field is empty. ID here. Oh, okay, nice. Oh, I need to add it. Let's go. Is there... I need to add these cards in. Yeah, especially these ones. Okay, let me add these cards in. I think it's pretty useful. Real quick, and then we'll take a break. High yield, Anki. We'll go PKA. Yeah. Command A, commands. Oh, well, not all of them, to be honest. Some I don't need yet, but these ones. Let's unsuspend those. And let's unsuspend this one. And I think let's suspend this one. I think that's it for now. There's a couple more we can do actually. Okay. Okay, I think we're good. Sure. Add those. And then let's sync it. Hold on. Oh yeah, okay. Yeah, that's good. Perfection. Alright, let's take a break. Oh, Lady Dunia. How many courses will you study? Okay, when you catch me, grab many sessions because I'm going to turn off the sound. Sure, maybe I'm too loud. We're gonna do read high yield grade. High yield for amino acids. Related, etc. Stack. Just adding new cards. And then let's see if we can do 3 more sections for today. I guess let's see if we can get up to enzyme kinetics. Enzyme kinetics. So we can finish enzyme kinetics. Yeah. Got those cards. Something like that. We'll see. It's kind of quite a bit, huh? Quite a bit. Yeah, I think I wanted to review the content as well. It might have been on there, so just kind of review it again. I don't want none of that diabetes mellitus. What's up with the light? It's so dark in here. Yeah, I don't know if it's there, but whatever. All right, let's go back. We're back. All right, where was I? Okay, I'm reading how you. Mm. Yeah, pH drops from PKE. This becomes protonated. This is- Let me see if I'm understanding this correctly. Okay. Peak at 50%. Oh, I see. It's irrespective of the given pH in the environment. It's just what it is. Gotcha. Gotcha. Okie dokie. Okay, let's make sure that we have the properties of this down a little bit. glycine nonpolar, leucine nonpolar, alanine nonpolar, methionine nonpolar, valine nonpolar, isoleucine nonpolar, proline nonpolar. Okay. Serine 309 cysteine. I think there's serine 309, serine 309 tyrosine, serine 309 tyrosine. Oh, serine 309. It wasn't cysteine? Serine 309 tyrosine. Yeah, okay. Glutamine, 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 serine, cysteine, asparagine 309, 309, polar, okay. Tryptophan, tyrosine, phenylalanine. Here we go. Negatively charged. Jesus, man. I'm starting up again today. And amino acids positively charged. Yeah. Alright. Oh, there's a way to quickly memorize this. 11 and 12. So let's take a look at it. And the pH is low. H plus sticks like glue. When pH is high, H plus says goodbye. pH is low, H plus sticks like glue. When pH is high, H plus says goodbye. 3, 4 carboxylic groups. 3, 4 aspartic acid and glutamic acid. 3, 4 carboxylic group. Carboxylic acid group. 4 aspartic acid. Oh. Carboxylic aspartic glutamic acid. What is the E? What is the E? Right here. Page. Carboxylic acid 4. 3, 6 histidine. 6, 8. I see actually. Okay, 3, probably so like 4. 4 aspartic acid and glutamic acid. Okay, 6 histidine, 8 amino group, 11 lysine, 12 arginine. Alright. The reaction creates H2O and fused to form peptides. Why doesn't it go on the peptide bond? To break the bond, you need water. Ooh, ah, ooh, ah, ooh, ah. That's why I remember that. Ooh, ah, ooh, ooh, ah, ooh, ah. Ooh, ah, ooh, ah. Oh, really? I just remembered it. You are annoying. You are gross. You go away. You are annoying. You are gross. You go away. You're annoying. You are gross. You go away. You go away now. Which amino acid belongs in a protein strand, depending on the environment around it. Okay. That makes sense. I'm looking at the positively charged. I'm looking at H, K, or R. Okay. Perfectly with aspartate. Perfectly with aspartate. Aspartic acid, negatively charged, the site 1 and 3. You want to substitute glutamate. Right? Oh, I want to put on some long pants. Okay, I'll be back. Hold on. Oh, man. I'm so sore from yesterday. Oh. All right. Yeah, see, this is the good stuff right here. This is the good stuff. This is the stuff we need. This is the stuff we need. Amen. Lord, hallelujah. Successfully making a beta turn. Oh. So glycine also disrupts alpha helix. Sarin sips on a short straw with a hydroxyl tip. 309 is a tree, add OH and a methyl. Tyrosine is phenylalanine with an OH. D and E can also be phosphorylated if there's no better targets. This is called the phosphomimetic effect. Phosphomimetic? Phosphomimetic? What is it? Phosphomimetic. Let's take a look at DNA again. Come on, over here. Sure. Sure. Why not? Shoot, lost track. Okay, man. Salt bridge is the ionic interaction between positively charged amino acids. It's technically a combination of both ionic bonding and hydrogen bonding. DNR can make a salt bridge. DNR. DNR makes sense. Okay, R and K cannot. R and K cannot. That makes sense too. And G and L cannot. G? G and L. Wait, L? L? But yeah, that makes sense. Oh, G and L. Okay. Gotcha. I see what it is. I say what as. Gotcha. So we have a dummy. How did you know? Oh, really? Gotcha. Yeah, lysine, arginine. Oh, okay. So if we consider A, G, E, V, I, D, M, F, K, W. We only need to look for the ones that are ionizable. So we only need to look at the ones that are in this. So we need to look at the N terminus, C terminus, and the R groups. Okay, and that's it. So the N terminus of A, not including A, G, what was it? G, there's no E, E we do. E, V, V we don't. L or I? It's capital, so I think that's I. Sugar. I think that's I, so we don't. D, do we do? D is I. Aspartic acid. And we don't. F, phenylalanine, don't. K, lysine we do. And W, tryptophan we don't. But we consider the C terminus. So we just need to do NC, T, NC, I guess EDK, right? NEDKC. And then N is 8. E is 4. T is 4. K is lysine, which is 11. And C is 3. So if pH higher than pKa, if pH is high, H plus says goodbye. pH is low, H plus sticks like glue. Is that the same thing to consider? So if pH pH here is 7.4 and pH 2.4. Okay, yeah, that's what I thought. So pH is higher than pKa, then that's minus H plus. pH is less than the pKa, and let's add pH plus. So pH of 8 greater than, now pH of, so 7.4 is less than 8. So 7.4 is less than 8. So we're going to add 1, 4 less than 8. So we're going to add 1. Okay. 7.4. It's not less than 4. So we're going to subtract 1. And 7.4 is less than 11. Going to add 1. 3 is less than 7.4. So we're going to add 1, 0, 0, 1, 7.4, 4 plus 1. Is that true? Is that what it said? The charge is -1. Oh, I missed this one. Just we got -1. We got -1. -1. Let's see, at 2.4. Why is it +2? Alright, fine. Oh. Oh, gotcha. I have to take that into account. Oh, yeah. Gotcha. Wow. Enzyme structure and function. Enzyme structure and function. I think it's these. No, not really. I wonder if there's enzyme structure and function in this one. No, that's okay. I'll read it anyways. Suspend. Eat one. K is lysine. So I'm guessing C0. Oh. Oh, gotcha. Oh, okay. Mm, gotcha. K is lysine. +1 and C carboxyl, it's gonna be C. So 2.4 is gonna be 2. Oh, okay, I got it. Okay. Gotcha. That was a good one. Oh, I forgot a break. Great. Okay, so I understand 6 now, though. So that's good. Yeah, that's what I'm doing. We're doing it. All right, we got a break. 9 minutes something. All right. Let's put the plate downstairs. Okay. Pull yourself up by your bootstraps, son. Any comments? Yo, let's do this. Let's go. Let's go. Let's do it, buddy. Let's get some chocolate. We definitely have to do some exercise today. All right, just one. Come on, just one. It's not that bad. It's not that bad. Okay. Only two PKA. PKA1 is the carboxyl, PKA2 is the amino, PKA3 is the R group. Okay. In ascending order? Ascending order, least to greatest? Okay. I already did this. There we go. Master PK. So high yield. I think after this one, we'll go ahead and watch the videos, and then we'll come back. Henderson-Hasselbalch equation. The net charge rate of that. All its ionizable groups. So we have the carboxyl group, the amine group, the carboxyl group, the amino group, and the side chain R group. NH3 plus and COO minus. Identify the functional groups present in the amino acid structure. Okay. Look up the pK values for the ionizable groups. What? It says 2 here, and then here it says 3. Kind of strange. But okay. Around 2, and amino is around 9 to 11. 9 to 11. Sure. So we said pH. If the pH is high, the H plus says goodbye. If the pH is low, H plus sticks like glue. pH is low, H plus sticks like glue. And pH. High pH, so does this make sense? So at high pH, there's low amounts of protons, solution, resulting in deprotonated groups. H plus says goodbye, which means that we deprotonate. That makes sense. Low amounts of protons in solution, pH is high, So we're looking at a lot of hydroxyl groups essentially, right? So H plus says goodbye. Yeah, deprotonates. Okay. Low amount of protons associated with more deprotonated groups. Deprotonated groups. Low pH environment. High pH environment. Hydroxyl groups, something deprotonated groups. Deprotonate the groups. Deprotonate the groups. Results in deprotonated groups. Low pH environment. Like acidic environments. These are basic environments. These are acidic environments, which have high amount of free protons. High amount of free protons. High amount of free protons in solution. We are going to protonate the groups. Protonation. Protonate. Protonated groups. Okay. Pay close attention to the condition and the characteristics of each ionizable group. Basic groups, if the pH is higher than the pKa, but it's already a basic group, which carries a positive charge, we're going to deprotonate, and that means it's no charge. pH is lower than the pKa, the group is, if the pH is lower than the pKa, the pH is lower than pKa, it's already base solution, we're going to add a charge, positive 1. Acidic groups, if the pH is higher than the pKa, for an acidic group, it's already going to have a negative charge. And the pH is higher, we're going to give it a negative charge. That makes sense. Gotta make sure it makes sense in the brain. And for the acidic groups, if the pH is lower, H plus 6 like glue, it's going to carry no charge for an acidic group because it already has a charge. And so it's going to be 0. Yeah, okay. Let's go. Yeah, buddy. Oh, my back. Oh, that felt pretty good. Add up the charges of all ionizable groups. A positive charge contributes to +1 to the net charge, while a negative charge contributes -1. Avoid the common mistake. Polypeptides are a chain of amino acids. Only the first and last residues in the chain. Only the first and last residues in the chain have the amine and carboxyl termini, respectively. Amine, carboxyl. Jazz hands. The other residues have peptide bonds, which are a type of amide group. Amine and amide. Show me the amine. Amine, is that NH3 plus? I think so, right? Is amide NH2 plus? It's been a while, so that's a cocaine. Survey says, not really. That's not the way to think about it. Oh, is it? Is it? Or is it not? I think it is. Sort of. Oh, it is. Okay, yeah. Great. Let's go. Maybe. Maybe not. Not really. Sure. Anyways. And not ionizable. What am I going to do? Do not. So you do not have to worry about adding them to the calculation. Well, I guess. I mean, can we look at this again? Okay, sure. All right, buddy. All right. Stop. Wait, no, stop. I just met you. And this is crazy. I don't think that's how it sounds. Anyways, let's watch the videos. Where you guys at? Window, this one. And this was like 2 minutes. 21 minutes. Oh, I don't know. I'll watch that third. And then
find isoelectric point or PI. Leah here from LeahForSci.com, and in this video, we're going to look at how to find isoelectric point or PI for amino acids. The isoelectric point comes from iso for amino acids. The isoelectric point comes from iso, meaning the same, and electric, meaning charge. The isoelectric point is the point at which the amino acid has the same charge, or rather a net charge of 0. In the last video, we saw how to find the charge for glycine at different pH values and called this structure when we have a plus and minus on the same molecule as zwitterion. Notice that in this form, we don't have no charge, but rather we have a charge of +1 and -1 that cancel out to give me 0.
Correctamundo. Okay. Continue.
If this is the structure where we have an isoelectric point, then the PI is really the pH of I, meaning the pH at which we have a net charge of 0. In the last video, we looked specifically at the charge for glycine at a pH of 1, 7, and 13. At a pH of 1, we got a net charge of +1. pH of 7, we got a charge of 0. And pH of 13, we got a charge of -1. If the pH 7 gives me a charge of 0, does this mean that the isoelectric point is 7? And the answer is no. pH of 7 is simply an estimate where it could be slightly greater than or slightly less than with an average charge of 0. The PI is a more specific calculated value, and so we have to look at how to find it mathematically. Let's prove it by adding one more value and finding the charge at a pH of 8. Don't forget that we have two pKa values for glycine. pKa for the carboxy is equal to 2.3,
Okay.
and pKa for the amine group is equal to 9.6.
Okay.
If we're looking at a pH of 8, we have to compare the pKa to the pH, remembering that the higher one wins. The pKa wins a proton for team molecule. The pH wins a proton for team solution. For the amine group, the pKa is greater than the pH, and that
Okay, wait, hold on, madame. Hold on, madame.
wins. The pKa wins a proton for team molecule. The pH wins a proton for team solution. For the amine group, the pKa is greater than the pH.
She says it's going to be 9.6. I don't know where she got that, but that seems accurate. Because it's at 8 and it's at 9 to 11, so somewhere around there. So that's okay. Okay, so pKa 9.6 greater than 8. So we're going to broken up the groups, but we're looking at the amine group right now. So it's going to add a charge.
And that means the pKa wins a proton for team molecule. The molecule is protonated, and we have a charge of +1 on the amine group. Looking at the carboxy, the pH is much greater than the pKa.
This is for amine group. And then for 2.3, 2.3 is less than 8. 2.3 is less than 8.
And the pH wins the proton for the solution, which means we take it away from the molecule. The carboxy group will be deprotonated.
Deprotonated, so we're going to subtract 1.
For a charge of -1.
What's the rule? There's a rule. Maybe it's better just kind of memorize the rule. But it's kind of similar to the logic I have, I guess. You won't be able to memorize everything all the time. But I think it was here somewhere. It was here. I think that's not okay. Maybe here somewhere in the beginning. Oh, I think it was this one. Whatever. Why was I looking at that one? Oh, right here. Okay, so pH, pKa. pH greater than pKa. pH greater than pKa. Fewer H plus. Deprotonated. Okay. Negative charge, positive charge. Yeah, I mean, it's the same logic. I was just making sure. Alright, we're good. Let's continue.
If we add them up, we have plus 1 minus 1 equals 0. So which is it?
So at pH 8, pH of 8, glycine is equal to 0.
Is the pI going to be a pH of 7 or will it be a pH of 8, given that both of these pH values give us a net charge of 0? If an amino acid does not have an ionizable side chain, that means it only has 2 pKa values, one for the carboxy, one for the amine, then you simply take the average of the 2 pKa values, which is pKa1 plus pKa2 divided by 2.
pKa1 is the carboxyl group.
To find the pI for glycine, we add 2.3 plus 9.
pI of gly. Yeah, gly is equal to 2.3 plus
9.6 and divide
6, which we're going to round off to 10, 11, 12. We'll round to 12, divide 2 is 6.
divided by 2. Remember on the MCAT you have no calculator, so we'll use the round up and down trick from the MCAT math series link below. 2.3 rounds down to 2, 9.6 rounds up to 10, 2 and 10 is 12, divide that by 2 and I get 6.
Okay.
The calculator gives me a value of 5.95, which on the MCAT is close enough.
Sure.
Notice that 5.95 or 6 is less than 7 and less than 8.
Less than 7 and less than 8, yeah.
But it is that range where we have a charge of 0, and the isoelectric point gives us an exact calculated value.
Gotcha.
That method is great when the amino acid has only 2 pKa values.
Okay. Which method?
But what happens if we have 3? For example, in tyrosine here, we have the
Pause. Continue.
carboxy and the amine that can gain or lose a proton, but we also have an ionizable side chain where the oxygen can lose a hydrogen. If we have 3 pKa values, do we average all 3?
Pause. pKa1, tyrosine, we got 2.2. pKa2, we have 9.1. 2 amine, no group, 3 carboxyl group. pKa3, we have 10.1.
If we only use 2, which 2 do we use? Before I show you how to do this mathematically, I want to show you logically so that you understand where we're getting the values. Remember, to find the pI, we need to know exactly where the molecule is going to have a net charge of 0. If we compare the pH to the pKa values, to find the pI, we need to know exactly where the molecule is going to have a net charge of 0. If we compare the pH to the pKa values, you'll be able to figure out when it's protonated or deprotonated, and you can do the guess and check method, where you randomly pick a pH and determine what the charge is going to be. Or you can go through this logically. I'm going to show you how to write it out, but on the MCAT, you should be able to do this in your head. We're going to rank the pKa values from low to high. So we have 2.2, 9.1, and 10.1. Remember that when the pKa is greater than the pH, the pKa grabs the proton for the molecule.
pKa is greater than the pH. And that means we have a low pH. That means it's acidic, it's going to protonate.
When the pH is greater than the pKa,
then that means it's basic. We're going to deprotonate.
pH, the solution grabs one from the molecule for the solution, meaning it's deprotonated.
Okay.
So if we were to compare what the molecule looks like in between the pKa values, you'll notice the trend. Start out by fully protonating the molecule and finding the charge. How do you fully protonate? You drop the pH well below the first pKa value. If the lowest pKa is 2.2, let's drop the pH to 1.
Okay.
At a pH of 1, every pKa is greater than the
at a pH of 1, every pKa is greater than the pH of 1 is really acidic, we are going to protonate.
The pH, meaning every group is protonated. So we get a hydrogen for a neutral charge, a hydrogen for a positive charge, and another hydrogen neutral. Fully protonated, we get a charge of +1. Remember the trick I showed you in a previous video, where as you raise the pH between pKa units, the charge goes down by 1, down by 1. If we raise the charge to the next in-between value, meaning above the first pKa, we're going to lose 1 proton and the charge will drop from +1 to 0. Which one do I deprotonate first? Well, if the pH is
it's going to drop to 0. Okay.
somewhere in between, let's set it to 5. That means the pH is now greater than this pKa value. The pH wins the battle of the proton and steals it for the solution. That gives me a -1 over here. That's how we get 0. +1, -1, and 0 for a net charge of 0. If we were to raise the pH greater than the next pK value, in this case we have to go in between
2.2, 2.2, pH 5 is greater.
between 9.1 and 10.1. For example, a pH of 9.6, we're going to get a half protonated deprotonated value for the 9.1 and the 10.1. But again, the trick is we drop the charge by 1, that's -1, and raising it well above 10.1. For example, pH is
It's -1. -1. 0. Yeah, 0. -1.
equal to 13, it should be -2. Let's prove it by showing what it looks like at 13. pH 13 is greater than 2.2. The pH wins 1 for the solution. We have a deprotonated.
Yeah, at 13. Yeah, deprotonated. Okay.
Carboxy with a charge of -1.
-1.
pH 13 is greater than 9.1, so we deprotonate, get NH2, a lone pair but no charge.
Right.
pH 13 is greater than 10.1, so we deprotonate the alcohol and get a charge of
-2.
-1.
Oh,
If
sorry,
we
yeah, -1. For a total of -2.
add it up, we have -1, -1, and 0 for a charge of -2 as we predicted. How does this help us figure out the isoelectric point? The isoelectric point is the average of the two pKa values that are just before and just after 0. If
Just before, just after 0.
the guesstimate here of pH 5 gives us a charge of 0, that means that when the pH is equal to the pKa at 2.2, we would expect to have the charge of +1/2. When the pH is 9.1 at the next pK value, we would expect a charge of -1/2.
Okay.
and the in-between of plus a half and minus a half is 0. So if we take the structure in between those two pKa values, that is where we expect to see the isoelectric point. To figure this out mathematically, we simply say that the pi is equal to 2.2 plus 9.1 divided by 2. Remember, without a calculator, we're going to estimate. In this case, it's easy to add the exact values. 2 and 9 is 11. 0.2 and 0.1 is 0.3. Divide that by 2. This is difficult to do, so we can round this up to 11.4. 11 divided by 2 is 5.5. 0.4 gives me 0.2, and that means we have 5.7. If that was too hard for you, just round 11.3 up to 12, divide that by 2, and you get 6. Knowing that you rounded up, your answer should be rounded slightly down, and 5.7 is slightly less than 6. Many professors will teach you to simply take the two closest pKa values and average them. So I want to show you why that's incorrect. The two closest pKa values for tyrosine are 9.1 and 10.1. If we take the average of 9.1 and 10.1, we get 9 and 10, which is 19.2, and we divide that by 2. Let's estimate. Let's round it up to 20 divided by 2 is equal to 10. Let's see what happens to this amino acid at a pH of 10. pH 10 is greater than 2.2, wins 1 for the solution, we deprotonate and get a -1. pH 10 is 1 greater than 9.1, we're going to estimate that it's an exact protonation, deprotonation instead of looking at the buffer zone. 10 is greater than 9, deprotonate, win 1 for the solution, and that gives me a neutral nitrogen. And finally, at a pH of 10, 10.1 is close enough, we can put this at a buffer. So it'll be somewhere between -1 and 0, because it'll be an H or a negative, and that gives me -1/2. Keep in mind, we estimated, but we only estimated a little bit. And when we add these up, we get a -1 for the carboxy, 0 for the nitrogen, and -1/2 for the ionizable side chain. This gives me a net charge of -1.5, which even with a slight margin of error for our estimations is still not 0. That means this is not the isoelectric point. So that trick of averaging the two closest values doesn't always work, and if you memorize it without understanding, you will mess up. Can we prove that our calculated value is indeed correct? Let's see. 5.7, let's estimate that to 6 and see what the charge looks like. pH of 6 is greater than the pKa. pH wins a proton for the solution. And
Yeah, negative deprotonase.
we get a -1.
Okay.
pH of 6 is less than the pKa of 9.1. The pKa wins 1 for the molecule, and we have a protonated amine for a charge of +1. pH of 6 is less than a pKa of 10.1, and the pKa wins 1 for the molecule, giving us a protonated
6. Yeah.
side chain. When we add up the charges, we have -1, +1, and 0 for a net charge of 0, which is what we expect.
Oh, okay, man.
I have some toast coming.
Okay. But that's kind of a lot. I need to just memorize it quickly. A little bit more quickly.
At the isoelectric point. Now that you understand how to do it, let's see the trick when you're given 3 pKa values for an amino acid.
There you go. Give me the trick. Give me the trick, please. I want the trick. I want the trick. Oh, I guess this is.
When you protonate the R group, or the amino acid side chain, you have 2 outcomes. If the atom that gets protonated is oxygen or sulfur, you're going to get a neutral protonated group.
Wait, what did she say?
Oxygen or sulfur.
proteinated, so have a pH value that's less than the pKa value.
You're going to get a neutral protonated group. You'll see that this for your acidic amino acids, aspartic acid, and glutamic acid. You'll also see it for the non-acidic basic ionizable side chains.
Okay, Mom, thank you.
You're welcome. Enjoy.
Thank you.
Cysteine and tyrosine. If you protonate the R group that has a nitrogen, it's going to get a positive charge, and these refer to your basic amino acids, which include histidine, arginine, and lysine.
HKR, HRK.
If you're not comfortable with this, look at the structures, protonate all your side chains, and find the charge of that variable group. The two options we're comparing are 0 versus +1, where 0 is lower and +1 is higher. If the protonated side chain is neutral for a charge of 0, it's the lower value. You're going to use the lower two pKa values. If the protonated R group is +1, that's the upper. So you're going to use the upper two pKa values, the lower two pKa values. If the protonated R group is +1, that's the upper. So you're going to use the upper two pKa values. That means for aspartic acid, glutamic acid, cysteine, and tyrosine, you're going to use the
Use lower P.
pKa of the carboxy group and the side chain. For histidine, arginine, and lysine, you're going to use the pKa of the amine group and the side chain. And that is how you're going to get your isoelectric point. Let's prove this trick by looking at aspartic acid for our neutral protonated group and lysine for our positive protonated group. Aspartic acid, or aspartate, has a CH2 followed by a carboxy in its side chain. pKa values will differ depending on the book or source you're referring to, but the concept is the same. So just look at the values you're given and apply the same trick. The pKa for the carboxy side chain is 2.1, amine side chain is 9.
Mm.
8, and variable group is 3.9. The trick is, when the protonated R group is neutral, we use the lower two values. If we protonate the side chain, we get an OH, which has no charge. So let's see what the lower two values are. The PI is equal to, the lower two values would be 2.1 and 3.9. We'll round 2.1 down to 2, 3.9 up to 4, 2 and 4 is 6, divided by 2 is equal to 3. We expect the PI to be 3. Let's prove it by finding the charge of this amino acid at a pH of 3. When the pH is 3 and we compare a 2.1 pKa, the pH is greater than the pKa and wins 1 for the solution. We're still in the buffer zone, but we're going to estimate a complete deprotonation for a charge of -1. At a pH of 3, the pKa 9.8 is greater than the pH, wins 1 for the molecule, and we get a protonated NH3+, giving us +1. And finally, the pKa of the side chain is greater than the pH of 3. We're still in the buffer zone, but we're going to estimate a complete protonation. When the pKa is greater than the pH, we win a proton for the molecule, giving us a charge of 0. If we add them up, -1 plus 1 plus 0 gives us a net charge of 0, which is exactly what we expect for the molecule when the pH is equal to the isoelectric point. In case you need to see it the long way again, let me show you the trick written out. We line up the pK values. We have 2.1, 3.9, and 9.8. If we drop the pH to 1, it's lower than the lowest pKa. Everything would be fully protonated. This would be +1, this would be 0, and this would be 0. We get a net charge of +1. If we jump to the next value, we would drop from +1 down to 0, down to -1, down to -2. We get 0 in between 2.1 and 3.9. That means we averaged these two to get the PI, which is exactly what we did. For our upper example, let's look at lysine, which has 4 CH2. We did.
Oh, above and below the net zero charge. There you go. Alright, that's not too bad. We'll watch the video one more time, and then we'll move on. I think I got
example, let's look at lysine, which has 4 CH2 groups in its side chain and an amine group. We'll write it as NH2. The pKa values are 2.2 for the carboxy, 8.9 for the parent amine, and 10.8 for the R group.
Pause it. Okay. Practice time. Should we for now? Okay, so we got lysine. Put them in ascending order. So we're gonna do 8.9. Oops. Oh, oopsie. Whoopsie daisy. 2.2. 8.9. 10.8. Oopsie, that should be there. Goodness gracious. 10.8. And then I just picked the pH value, right? Yeah, I think I just arbitrarily do it. So we'll do pH of 1. We'll do pH of 5. pH of 9.5. And a pH of about Let's do 11. I guess let's try it out again. HNHCO NH2 10.8 on the R group, 2.2 on the carboxyl group, 8.9 on the amino group. So I think these are total net charges, so I have to do it of the whole thing. So at pH of 1, it's less than 2.2. So it's going to be very acidic. It's going to protonate. So we're going to get +1 here. Yeah, one of these. A +1 here. And +1 here. Right or no? But I think this is going to be neutral. This is going to be neutral, and then we'll have a +1. So it's actually just going to be +1. Let's see what she says. I think we can only add it to the R group. It's going to be 0, and it's going to be 0 as well.
Since lysine, when protonated, will give me NH3+, or an upper value, we have to average the upper two pKa values to get the isoelectric point. Pi is equal to 8.9 plus 10.8.
Okay, lady. Just let me get there. Hold on. And then pH of 5. pH of 5. We're going to take away. So it's going to be -1. pH is less than pH is less than the pKa. we're going to add 1 into 10.8. Five is less than 10.8. So the pH is less than, we want to add 1. So we're going to get this one here. 8.9, we're going to get 9.5. 5, 9.5. pH is greater. So we're going to do -1. Okay, we're going to do -1 again. So this is going to be -1. Did I do that right?
Hydrogen on and steals it for the solution, that gives me a -1 over here. That's how we get 0. +1, -1, and 0 for a net charge of 0. If we add it up, we have -13. We added up the charge 1 and so we on and steals. If we
Thought I got it. You did. HN, I think. Maybe there is another one also. Because you know it well. And there is nothing coordinated. H and H. That used to be like that neutral. Supposed to be NH2. Okay, let's try it again. Two point two. pH of 1. It's going to protonate. It's going to protonate, so we're going to have NH3 plus, which will be a +1. Going to have OH, and we'll have an OH, so that's neutral. We'll have NH3 plus, so we'll have +2. Why did you write HN? Let me see. The primary amine. Yeah, because, okay, that's kind of where I messed up. So, I think this should be NH2. If it's NH, then if you protonate, you're going to get a neutral. charge, and that's gonna mess up. Well, that's gonna mess up the. You trying to find the average for the isoelectric point. She did it just based off that trick, but you know, if you don't have the trick, then if you don't remember a trick, then doing it the regular way, she messes up. Anyways, let's continue. All right, so pH equal to 5. We're going to have a -1 here. We're going to have a +1 here. And we're going to have a -1 here. So that's -1. Make sure. Wait. Yeah, -1. Oh, and the pH is low. -1 +1 +1. Well, +1. And then I'm guessing then well, just based off the way it's flowing, right? pH equal to 9.5. We'll have -1 here. Then we'll have -1 here. Then we'll have +1 here, and that's -1. Let's take it from above or below the net zero charge. Okay. Each and 5 the charge of Okay, he continues. Gotcha.
9.1.
Okay, never mind. It's gonna be +1 here, so NH3 plus, and then this is gonna be NH3 plus, and then this is gonna be O minus. That's gonna give us a +1 here. Then for 9.5. We're gonna get a +1. Minus 1. And 0. And we'll have 0 here. So that'll give us 0. I'm going to take it below and above the 0. So that's going to be 8.9 and 10.2. Oh, 10.8. Which is going to be like +9.
Did both values up, which means it wins one for the solution, deprotonate the molecule, and get a charge of -1. A pH of slightly less. The pH is greater than the carboxy pKa, which means it wins one for the solution, the charge of another protein -1. And 0, when we add it up with the fully protonated at a pH of 1, we would have a protonated nitrogen, another protonated nitrogen that's +2, and 0 for the carboxy side chain when it's OH. That would give me a charge of +2 fully
Yeah, that's what I got.
protonated. Jump to the next pKa value, you'd get a charge of +1 because we drop a point. The next one gives me 0, and fully deprotonated would give me -1. When the pH is somewhere between 8.9 and 10.8, we have a charge of 0, and this is what we expect to average to get the isoelectric point. This is what we used to get a pH of.
I wonder if you start with 2, then does that mean you automatically will drop? I think so, right? That makes sense.
Of just under 10 with a molecule have.
Yeah, she started it here with an NH, but it really should be NH2 and neutral. Protonated at pH 1, NH3, NH3 plus. Add a charge, and this will be 0, and it'll be cool. We add the H, then that's plus 2, and then
2 plus 2H.
if it's plus 2 here, this is 1, this is going to be 0, it's going to be negative 1. So 0, I'm going to take these two. Sure.
Find the charge and iso quiz and cheat.
Okay. I guess so. Oh, Jesus. Let's take a break. I guess. Well, yeah. Will the figure show the molecule with the pK values? Yeah, that's fine. That's all I need. Sure, that's fine. Okay. I'll watch the videos. Well, actually. Yeah, we'll get to 76 and then I'll watch the videos. on the next one, and then what was that? And then we'll do Anki. Serine 309 and tyrosine. Serine 309 and tyrosine. DNR. D aspartic acid. R arginine. Yeah. Okay. Yeah. So it will most likely give me some sort of structure. Cool. All right. Yeah. 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 Mm. And to get you guys to show what I'm watching too, right? This one.
This is MSJ Chem. In this video, I'll be looking at the stereochemistry of amino acids. As you may remember from the previous video, a chiral carbon atom is a carbon atom bonded to 4 different atoms or groups. Amino acids are optically active, with the exception of glycine, and exist as enantiomers. Here we can see the 2 enantiomers, or as you may remember from the previous video, a chiral carbon atom is a carbon atom bonded to 4 different atoms or groups. Amino acids are active, with the exception
Hold on.
This is MSJ Chem. In this video, I'll be looking at the stereochemistry of amino acids. As you may remember from the previous video, a chiral carbon atom is a carbon atom bonded to 4 different atoms or groups. Amino acids are optically active, with the
exception of glycine.
And exist as enantiomers. Here we can see the 2 enantiomers, or stereoisomers of the
Alanine.
amino acid alanine. The chiral carbon atom, which is shown with a red asterisk, is bonded to 4 different atoms or groups. The 2 enantiomers are mirror images of each other, and they rotate the plane of plane.
All right, so the nitrogen is coming at me, hydrogen's away, carbon's just facing behind, and so is the carboxyl group. So we got this going on, okay? And this one, we have nitrogen coming at me from the right side, facing that way from the other side. Can we rotate? I feel like we could rotate.
Polarized light in equal amounts but in opposite directions. The Korn rule can be applied to name the 2 stereoisomers. When using the Korn rule, the molecule is viewed with the hydrogen atom facing away from the viewer. If we give the carboxyl group the letter CO, the side chain the letter R, and the amino group the letter N, we can see it spells Korn. If the Korn is spelled clockwise, it is the D isomer.
Oh, really? Oh, that's pretty cool. Hey, that's pretty cool. Clockwise. Clockwise, we got D. Counterclockwise.
Korn is spelled counterclockwise. It is
L?
the L isomer.
If the Korn is counterclockwise. Korn.
So if we look at the isomer on the left, the Korn is spelled counterclockwise. Therefore, it is the L isomer. And if we look at the isomer on the right, the Korn is spelled clockwise. Therefore, it is the D isomer. So the names of these isomers are L-alanine on the left and D-alanine on the right. The proteins in our bodies are only composed of the L enantiomers of amino acids. This means that 19 of the 20 naturally occurring amino acids exist as L enantiomers. The DNL convention refers to the optical activity of the enantiomers of glyceraldehyde. D-glyceraldehyde is dextrorotatory, and L-glyceraldehyde is levorotatory. This refers to the direction of the rotation of plane polarized light.
Sure.
Attached to 4 unique substituents. To find the chirality, we simply rank the unique substituents from high to low priority, put group number 4 in the back because we're only looking at the 3 highest, and then determine if we go clockwise or counterclockwise when tracing a path from 1 to 2 to 3. The groups are ranked following the Kohn-Ingle-Prelog system, which ranks them from highest priority atom, not group, just the atom attached, to the lower priority. While the periodic table has over 100 atoms, I want you to memorize these 10 because these will show up the most when you're studying organic chemistry. And specifically for amino acids, you're going to see carbon, hydrogen, oxygen, nitrogen, and sulfur. So without memorizing the entire table, recognize that in amino acids, the 5 atoms that we're ranking, sulfur will always be the highest, then oxygen, then nitrogen, carbon, and hydrogen. If you're faced with 2 of the same atom, cross that out and go to the next atom, and then determine again, is it sulfur, which is highest, then oxygen, nitrogen, carbon, hydrogen, until you find a point of differentiation. I know I'm going through this quickly, but that's because I taught it in great detail in the stereochemistry series linked below. Let's try an example. Here I have the line structure version for the alanine zwitterion. Alanine is an amino acid that has the carboxyl and amino group in its backbone. The hydrogen in skeletal structure is invisible, but it's right there in the back. And the R group, which is CH3 for alanine. The first thing we do is identify the chiral carbon, which is the alpha carbon in the backbone, and then rank the substituents. The atoms we're ranking are carbon versus nitrogen versus hydrogen.
So here we got our carbon, alpha carbon. Here we go C-O-R-N, C-O-R-N, right, clockwise, right, D.
Hydrogen versus carbon. Just in case you haven't memorized it, I'll let you cheat. Sulfur outranks oxygen, which outranks nitrogen, outranks carbon, outranks hydrogen. For alanine, we're comparing nitrogen, carbon, and hydrogen. Nitrogen is priority number 1. Hydrogen is priority number 4. The alpha carboxyl and methyl group both have a carbon, so how do we know which outranks which? If you remember the trick I taught you, whenever you have a methyl in the presence of a hydrogen, it's automatically going to be priority number 3. Or you can do it the long way and recognize that if the 2 carbon atoms cancel out, the next highest priority on the carboxyl is an oxygen, the next highest priority on methyl is a hydrogen, and since oxygen outranks hydrogen, the carboxyl is priority number 2 and methyl is priority number 3. Group number 4 is in the back, so we cross it out, trace the path from 1 to 2 to 3, and since the top of the arc goes to the right, this is an R amino acid. R and S are enantiomers of each other, and the swap method.
Wait, is that what the other video said, or am I tripping?
This is MSJ exception of clock atom, which is shown with a red light from the viewer. D is spelled to clock, therefore it is the L isomer. L alanine composed of the L enantiomer. The DNL convention refers to the optical activity aldehyde.
Oh, no.
This
Method is when you swap one group to get the enantiomer.
Good. It's D now. So anyways, we have D, torn, D.
This means if I swap the position of the methyl and the hydrogen so that the hydrogen atom is coming forward and the methyl is going back, I expect to have the S version of alanine. Let's prove it. Nitrogen is priority number 1. We've already proven that carboxyl is number 2, methyl is 3, and hydrogen is 4. In this case, hydrogen, which is number 4, is coming forward. So we're going to treat it the same way, but then reverse the direction to compensate for hydrogen not going towards the back. We cross out number 4, trace the path from 1 to 2 to 3, then reverse the direction because group number 4 is forward and we have to flip the molecule. And this gives me the S enantiomer as predicted. You have to know 20 amino acids, but only 19 of them are chiral. The amino acid glycine has hydrogen as its variable group. So if we show a hydrogen that came with a backbone, and then another hydrogen for the variable group, to find the chirality, we rank nitrogen as number 1, the carboxyl as number 2, but which hydrogen atom is number 3 and which is number 4? The answer is neither. Because we have 2 of the same substituents, that means we do not have 4 unique groups on carbon, we have 3 unique groups. The molecule is symmetrical, and with symmetry, we get achirality. This makes glycine achiral. In organic chemistry, you focus mostly on RNS, but with biological molecules, we prefer to put it into a Fisher projection where we can find RNS or the other system, D and L. RNS is used to find the absolute configuration because it tells us the absolute order of priority groups. DNL tells us the relative configuration because we see the relative relationship between this amino acid and DNL sugars, specifically the small sugar glyceraldehyde. Fisher projections initially came about as a way to represent a chiral sugar in a simple form. The convention for a Fisher projection is to have a carbonyl on top of the molecule, and the lowest OH group, if it's to the right, tells me I have a D sugar, and if it would be to the left, tells me I have an L sugar. If we want to show amino acids in a Fisher projection, the first thing we want to do is find the OH group. But amino acids don't have an OH group. They do have a carbonyl, which we can put at the top. But what do we use to determine if it's D or L? If we don't have alcohol, we're going to use the amine group, the nitrogen, instead. The convention for amino acid Fisher projections is to use the nitrogen to determine if that amino acid is D or L. If we put the nitrogen to the right, that will give me a D Fisher projection. If we put the nitrogen to the left, that will give me L. Just like sugars, we put the carbonyl on top. I remember this as a tall carbonyl. It needs to stand up, and it stands up at the top. The R group is the variable group. We always draw it on the bottom, so in Fisher projections, it's no different. We still draw that at the bottom. And that means the hydrogen is the atom that swaps positions with the amine group in the DNL amino acids. Even though we have potential for two types of amino acids, biological molecules will prefer the L form rather than the D form. And the way that I remember this is that our bodies like the L form of the amino acid, and they don't like the D form. Now that we understand the convention, let's turn this molecule, which we already showed is R-alanine, into a Fisher projection. This is where it gets tricky. I'm going to show you how to do it once, but I really don't want you worrying about this because I'm going to show you a trick later to quickly figure out if D or L is R or S, and then you won't need to interconvert this way. Remember that with a Fisher projection, Mr. Organic Chemistry helps us remember that the horizontal bow tie lines are coming forward, and then the vertical spine is going back into the page. There are a couple of ways to put this onto a Fisher projection. I'm going to go with the simplest and then rotate it so it looks like how we want it. If we push that hydrogen up a little so that it's still in the back of the molecule, that will push CH3 into the page as well. That would give me a hydrogen at the top, a CH3 at the bottom, a carbonyl still to the right because that didn't really move, and the amine group to the left. But this is not in the convention that we want. The first thing you want to do is prove to yourself that you converted into the correct Fisher projection, and that means finding RNS. Remember, nitrogen is 1, carbonyl is 2, methyl is 3, hydrogen is 4. Group number 4 is down, just like Mr. Organic Chemistry's spine. We trace a path from 1 to 2 to 3, which gives me R. We know we're correct, but it's not the ideal Fisher projection. To put this into correct form, we can either rotate the molecule or use the swap method that I teach in the chirality series. The R group is in the right place. CH3 is at the bottom. Nitrogen can be right or left for DNL, so that's fine. But hydrogen and carbonyl are in the wrong place. So the first swap we're going to carry out is moving the carbonyl to the top and hydrogen to the right. That's one swap giving me an enantiomer. I need to do a second swap to retain the chirality of the starting molecule. And since I can no longer move the carbonyl and I can't move the methyl, I'll go ahead and swap the hydrogen and the amine. We'll bring the amine group to the right, hydrogen to the left. That gives me 2 swaps, which is an even number, same chirality as the starting molecule. I'll redraw it with the amine on the right, carbonyl at the top, and hydrogen on the left. Since nitrogen is on the right, everything else is set up the right way. This is a D amino acid. R-alanine is a D amino acid. Are you feeling overwhelmed right now? I would be. On an exam where you need to quickly come up with answers, you definitely don't have this kind of time. So I want to show you something. The second option is the guess and check method. Let's set up R-alanine as a random Fisher projection, and then on the Fisher, determine if it's R or S. We know the R group has to be on the bottom, so we'll put the CH3 here. The carboxylate must be on top, and I'm randomly going to guess that the NH3 is on the left and the hydrogen is on the right. Let's see if we did this correctly by prioritizing. Nitrogen is 1, carbonyl 2, methyl 3, hydrogen 4. Number 4 has to be on the bottom. If it's not, then if the circle appears R, it's S. If the circle appears S, it's R. We cancel out number 4, trace the path from 1 to 2 to 3, and then reverse it because group number 4 is coming forward. And this gives me S. This tells me I guessed incorrectly. So all I have to do is one swap. Bring the hydrogen to the left, bring the NH3 group to the right, and that would give me the R and therefore D alanine. This is a much faster way, but I have an even faster way that I'll show you at the end. First, let's try 2 more examples. Let's take a look at L-phenylalanine. L tells me the NH3 group is on the left, a hydrogen is on the right, carboxylate is at the top. You should have your amino acid side chains memorized. Phenylalanine is a phenyl group on alanine. Alanine is a CH3, so we make it a CH2. We remove a hydrogen and attach a benzene ring to give me phenylalanine. The 4 atoms we're comparing on this molecule are carbon, nitrogen, hydrogen, and carbon again. Carbon, nitrogen, and hydrogen. Nitrogen is the highest priority, that's number 1. Hydrogen is number 4. And then we have a choice between the carbon in the carboxylate or the carbon in the phenylalanine side chain. The carbonyl carbon has an oxygen. The R group carbon has another carbon as its highest priority. And since oxygen outranks carbon, the carbonyl will be number 2, the side chain will be number 3. We cross out number 4 and trace the path from 1 to 2 to 3. But since group number 4 is coming forward, we have to reverse the direction, and that gives me S. L-phenylalanine is an S amino acid. Now let's take a look at L-cysteine. Once again, for the parent, we have NH3 on the left for an L amino acid, giving me hydrogen on the right, carbonyl at the very top, and the cysteine side chain is a CH2 bound to an SH. For this molecule, we're comparing nitrogen, carbon, hydrogen, and carbon again, same 3 atoms. That means nitrogen is again number 1 and hydrogen number 4. On carbon, we now have to look for the next highest priority. The carbonyl has an oxygen, but the side chain has a sulfur. Sulfur outranks oxygen, making the R group number 2 and the carbonyl number 3. We cancel out group number 4, trace the path from 1 to 2 to 3, and then reverse the direction because number 4 is coming forward, giving me R. L-cysteine is an R amino acid. Now here's the trick. L-cysteine is the only R amino acid. All the other L amino acids are S, and I'm going to show you why through logic, and that way you'll never mix it up again. And then if you're given an amino acid in this form, all you have to do is determine R or S, quickly figure out if that's D or L, and then pop it onto a Fisher projection. So how can we know that cysteine is the only L amino acid that will be R? Ask yourself what it takes to get an R or an S amino acid. Every L amino acid has an NH3 group to the left, hydrogen to the right, and a carbonyl at the top. The R group is ultimately going to determine the direction. Nitrogen is always priority number 1, and hydrogen is always priority number 4. Here's the trick for L amino acids. If the carboxylate outranks the R group for an L amino acid, then you're going to get an S chirality. If the R group outranks the carboxylate, then you're going to get an R. If the R outranks, then you get an R. Let's prove it. For the first condition, if the carboxylate outranks the R group, let's make the carboxylate priority number 2 and the R group priority number 3. This means we cancel out 4, trace the path from 1 to 2 to 3, reverse the direction. That is S. That's the first condition. In the second condition, we said the R group outranks the carboxylate, making the R group 2 and the carboxylate 3. Once again, we cancel out number 4, trace the path from 1 to 2 to 3, and reverse the direction because 4 is forward. That gives me R. That's pretty simple. Here's the fun part. The only amino acid that has an R group outranking the carboxylate is cysteine. Think about what it would take to outrank that carboxylate. The amino acid side chains are limited to some combination of sulfur, oxygen, nitrogen, carbon, and hydrogen. To outrank the nitrogen, you would have to have another nitrogen and then a high priority group on that. None of the side chains start with a nitrogen, so this is locked in at position number 1. The side chains, except for glycine, all start with a carbon. So if we compare what's on the carboxylate carbon to the side chain carbon, we can figure it out. Carbons will cancel out, just like we saw in these last 2 examples. We had a C, and then we went to the phenyl group. We had a C, and we went to the sulfur. The next atom on the carboxylate is an oxygen. The only way for that R group to outrank the carboxylate it has to have something higher in priority than oxygen. For example, serine is a CH2OH, but the carboxylate has 3 bonds to oxygen. Serine only has 1, carboxylate wins. So if we've ruled out the possibility of nitrogen, if the carboxylate has the most bonds to oxygen, the only way to outrank the carboxylate is with a sulfur. There are 2 amino acids that have sulfur, cysteine and methionine. But if you think about the side chain for methionine, you have a CH2 bound to a CH2, and then finally you have this sulfur bound to a CH3. The C would cancel out compared to the carboxylate, but then the oxygen on the carboxylate will be compared to a carbon. You never get a chance to go as far as the sulfur, and so that doesn't count. But cysteine, as you saw in the last example, has a carbon directly bound to sulfur. This means it's the only R group that outranks the carboxylate. And so instead of seeing the rule as the R group outranking carboxylate is R, just think of it as the cysteine R group outranks the carboxylate and therefore is the only L-amino acid with R stereochemistry. So you're given a structure like this, you're asked to figure out its chirality and to show it on the appropriate amino acid Fisher projection. First, we have to identify what's going on. The amino acid has an alpha carbon attached to an alpha amine and alpha carbonyl, and a 2-carbon side chain with a carboxylate. This right here is our side chain. You should recognize this as the conjugate base of the shorter acidic amino acid, making it aspartate. The alpha carbon is the chiral carbon, so let's figure out if it's R or S. The amine is number 1. The invisible hydrogen is number 4, so we'll just put a 4 instead of hydrogen. The backbone carbonyl is always number 2, except for cysteine. And the side chain will be priority number 3. How do we know? Carbon versus carbon. The carbon on the side chain has another carbon. The carbon in the backbone has an oxygen. Group number 4 is in the back, so we cross it out. Trace an arc from 1 to 2 to 3, and we get S. S-aspartate, does that mean it's going to be an L or D amino acid? Let's go back to the trick. L amino acids are S unless they are cysteine. We're just reading this backwards. So if we have an S-aspartate, we instantly know that it's an L amino acid, and we draw it accordingly. The amine group on the L gets drawn to the left. The nitrogen number 4 is forward, so we cancel it out, trace an arc from 1 to 2 to 3, and then reverse the direction since 4 was forward. This is S, and because the NH3 is on the left, it's an L amino acid. Be sure to join me in the next video where we look at how to find the charge for amino acids and zwitterions to justify why I keep drawing them as a carboxylate and NH3 plus instead of neutral form. You can find this entire video series along with the amino acid practice quiz and cheat sheet by visiting my website, leahforsci.com/amino acids.
Oh. I need to put some eye drops on after this for sure. Sure. Okay. Oh, my belly. My belly. I already said it. When the fuck? To find the net charge, focus on isoelectric. Oh yeah, isoelectric points. This is translate. Okay. Identify ionizing groups. Determine pK values. Yeah. Okay, that makes sense. The net charge of an amino acid is the net charge of the amino acid. The net charge of an amino acid is the net charge. What are we talking about here? Oh, okay. Sum of all charges on atoms, including. Okay, yeah. Yeah. Okay. Proline is known for breaking alpha helixes and being kinky, disrupting rotation in the alpha helixes. Oh, okay. Beta turns. Mutations. Proteins. These can change the. This can change the blank in DNA. Genes, codons. Codons, yeah. Codons. Thymine, adenine, guanine, cytosine. Thymine is replaced by uracil. I think this was good. These codons tell the cell which amino acid to add next, and these codons tell the cell which amino acid to add next when making a protein. Codon AUG good. Peptide bond is formed between the uh, carboxyl group of the amino acid to the amine group of the new amino acid, and the in a condensation reaction, forming water, carbonyl carbons act as the electrophile. Amine group nitrogen. Amine group nitrogen of the amino acid is being added. I think that's good. Glutamate is ionic bonds. Ionic bonds donating electrons. Okay. Ionic interaction between positively, oppositely charged amino acids. You would expect only hydrophobic amino acids like glycine, leucine, alanine, cyanine, valine, isoleucine, proline. Oh, and phenylalanine and phenylalanine. Yeah, and phenylalanine in that portion. Well, I kind of miss phenylalanine. So to calculate PI, identify the ionizable groups and calculate the average of the two pKa's that are below and above 0. Oppositely charged amino acids is a combination of both ionic and hydrogen bonding. The isoelectric point refers to in gel electrophoresis when the protein no longer migrates, but it's essentially where we have where we find the pH. Wait, no. Where we find an average of the two central pKa's. Given a certain pH value, where the molecule's net charge is going to be 0. Yeah. Okay. Right. Yeah. Yeah. Yes, I think that's good. amino acids form peptides. Individual amino acids undergo a condensation reaction and fuse to form peptides, which are held together by something called the peptide bond, covalent bonding, hydrogen bonding. Covalent bonding, not hydrogen bonding. I think. Yeah, it's covalent bond. Are peptide bonds covalent bonds? Individual undergo condensation reaction, fused to form peptides. Covalent bonds. Covalent bonds. Yeah, covalent bonds. Proteins commonly phosphorylated are serine, tyrosine 309. Commonly phosphorylated to come down there, Billy boy. Commonly phosphorylated. Phosphomimetic effect. Let's be A, include tyrosine 309, and serine. Now, unregulate or downregulate. Upregulate or downregulate their function. Yeah, serine 309 tyrosine, phosphomimetic. Upregulate or downregulate their function. What does that actually mean, Dad? What are we talking about here? What are you talking about? Oh, increase the protein's activity or function. Gotcha. Upregulate, downregulate the function. Downregulation might shut off, change shape, or become inaccessible. More active, open up, or bind more efficiently. Gotcha. We'll go again, since I missed that one. We're taking a break. Taking a break here, lads. 10 minute. A 10 minute. Just a quick 10 minute. Maybe we can switch pants to the shorts. You know what I mean? that's right.
Anybody on the chat? Agnes. Oh, it's good. Looks like I was muted. Looks like I was muted.
Start the clock, boy. Start the clock, big boy. Sulfide bonds between the positive and negative charges of the R or side chain of the amino groups form together to make the tertiary structure of the protein. That's completely wrong. No, disulfide bonds are between cysteine and cysteine, and they go 1 to 4? 2 cysteine residues. Wait, what goes 1 to 4? Oh, that's alpha helixes. Hydrogen bonding. Never mind. Yeah, okay. I got it mixed up. Disulfide bonds, 2 cysteine residues can covalently bond to form disulfide bonds. But he can disrupt these bonds. Sure. Yeah, amino acyl tRNA synthetase. tRNA. Amino acyl tRNA synthetase. Yeah. Amino acyl tRNA synthesis. We add water. This is called condensation reaction or hydrolysis. Not dehydration, no. When we release water, it's condensation reaction. When we use water to break the peptide bond, it's called dehydration reaction. Sure. Yeah, okay. I think that's good. To find the net charge for all these steps, identify the ionizable groups. Identify the ionizable groups. Then take the average between the two. Take the average between the two central pKa's. determine PK values. Yeah. Determine PK values. Histidines PK is 6. The net charge of an amino acid is the net charge of the amino acid is adding up all of the ionizing, adding out all the charges for the ionizable groups. Right? Sum of all charges in an ionizable, including the amino group, the carboxyl group. Okay, yeah, yes, I mean, kind of what I said. Proline, known for breaking alpha helixes and being for breaking alpha helixes. Causing turns in beta pleated sheets. Glycine rotation disrupting the alpha helix. It's only amino acid in 1 of the 20 cycles. Beta turns. Yeah. I think it's good. I don't know if I want to get some chocolate. Segmentation effects, which are called mutations. These can change the codon in the DNA. No. Okay. This is the ionic bonds formed between the amino acids. Between the amino acids R group change. Between the oppositely charged amino acids. You would expect only hydrophobic amino acids like glycine, leucine, alanine, methionine, valine, isoleucine, proline, and phenylalanine. Proteins are commonly phosphorylated to upregulate or downregulate the activity of the proteins. The proteins. Amino acids that can be phosphorylated include serine, 309, and tyrosine. DNA can also phosphorylate in the absence of a better target known as phosphomimetic effect. Let's go. To maintain max protein function, an aspartate is not available except to the most common, which is glutamate. Peptide bond is formed between the
amino nitrogen of one amino acid, and the N and the carboxyl group of the other amino acid, as carbon often do. They act as the electrophile. Salt bridge in the context of proteins is an ionic interaction between oppositely charged amino acids is a combination of both ionic bonds and hydrogen bonds. Ionic bonds and hydrogen bonds hold together tertiary structure. To calculate the PI, first identify the two central pKa's, then calculate the average of the two central pKa's. Identify the ionizable groups, calculate the average of the two central pKa's. Isoelectric point focusing. The isoelectric point is refers to an gel electrophoresis where the protein stops migrating due to the fact that you found the pH at which the net charge is 0. At which the net charge is 0. Yeah, essentially. The exact pH value for an amino acid in a gel electrophoresis state. Multiple pKa's listed in descending order. Each of the pKa's are above or below the net zero charge predictor. I think that one's good. But it's the amino acid gel electrophoresis. Amino acid. Let's look at them. Individual amino acids undergo a condensation reaction. Meaning the reaction creates water and fuse to form leads, which are held together by something called covalent bonds. Peptide bond. Again, disulfide bonds. Cysteine. Cysteine residues. Yeah, it's two cysteine residues can covalently bond to form disulfide bond. Holding together tertiary structures. If sufficient cysteine residues are available, he can result. For the amino acids to be added to the growing protein, they need a little helper called tRNA. Think of tRNA as an Uber for amino acids, but for the amino acid to hop in the right Uber, regular by the driver. So a friend which is called the amino acyl tRNA synthetase. This enzyme checks if the amino acid and tRNA are a perfect pair. If they match, just stick them together. Difference of this for each amino acid and making sure that every tRNA carries the right passenger. Breaking peptide bonds requires inverse of gradient. We need to break the bond. We add water. This is called dehydration reaction, or even hydrolysis. We add water. Oh, this is called hydrolysis. That's fine. That's the same way. To find the net charge, follow these steps. Identify the ionizable groups. Identify the ionizable groups. Determine the net charge. one, identify the ionizable groups. 2, determine the pKa values. Memorize cystine's pKa is 6. Now let's go. Net charge of an amino acid is the net charge of an amino acid is the summation of the charge of the carboxyl group, the amino group, and the R group added. Summation here. Cell bridge in the context of proteins is a salt bridge. I'm not sure. Salt bridge. Oh, okay. Iron again actually do oppositely charged amino acids. The peptide bond is formed between the amino group nitrogen with the one amino acid, which acts as a nucleophile, and the carboxyl group of the other amino acid, which act as the electrophiles. And the carbonyl carbon. Act as electrophiles. And this is made possible through resonance of the valence electrons. Okay, I think that's good. Isoelectric point is it's is when in electrophoresis the exact pH value is found. The exact pH value is determined for that amino acid to have a net zero charge for it to stop migrating. That's good. Individual amino acids undergo a condensation reaction fused to form peptides, which are held together by something called the peptide bond. Salt bridges in the context of the protein is bonded between oppositely charged amino acid R groups. Anionic interaction. Right, okay. Which are called mutations. These can change the codons in DNA and lead to the wrong amino acid being added to the protein, which can result in destruction. Yeah, that's good. Proline is known for breaking alpha helixes and being in beta turns due to its unique and rigid structure. Glycine sites any condition unique to rotation, disrupting the alpha helix. It's the only chemical common. Yeah. What is this? I don't know. I don't know about this card. There's nothing here. Let's suspend the card. What's wrong? The isolation one is the pH. Oh, what the heck? Let's put this down. The isoelectric point amino acid is the pH at which it carries no charge. No net charge. Yeah. Avoiding common mistakes. Polypeptides have I'm not sure. Oh, polypeptides have amine and carboxyl terminal only. Okay. You would expect only hydrophobic, like glycine, leucine, alanine, thionine, valine, isoleucine, proline, and phenylalanine. Proteins are commonly also related to upregulate or downregulate protein activity. Amino acids that can be phosphorylated include serine, tyrosine, and 309 and 309. DNA can also occur in the absence of a better target known as phosphomimetic effect. Upregulate damage function. Yeah, good. Polypeptides have an amine terminal, N-terminal, and a carboxyl or C termini only at the first and last residues. The residues between peptide bonds, which are amide groups and not ionizable. Yeah. Amine and carboxyl amide. The R start and stopping. Every protein making process has a start and stop. Start codon is likely to go in a race. Start codon is always AUG, and stopping are UAA, UAG, and UUA, AUG, AG, UGA. You are annoying. Wait. You are annoying. You are gross. You go away. Sure. Disulfide bonds. Disulfide bonds like two cysteine residues. The DNA uses words called codons. Wait. The DNA uses words called codons. In the active site with your negatively charged substrate, in the active site with a negatively charged substrate, you choose a positive amino acid like you choose a positively charged amino acid like histidine, lysine, or arginine. Go! Breaking a peptide bond requires the inverse of creating it, meaning to break the bond, we add water. This is called hydrolysis, or even a dehydration reaction, as the water molecule is used in the process of lysine bond. Let's go. A amino acid is a protein is the building block of life. Building block of life. It is molecule when in combination with other. No. A link is a building block. Is a molecule that when in combination with other amino acids can form a. An amino acid is the building block of proteins. It is a molecule that when in combination with other amino acids and other types of bonds can form a secondary, tertiary coordinate structure. Okay. An amino acid is a building block of proteins. The molecule that when in combination can form a peptide. Oh, okay, sure. tRNA. Enzyme amino acid tRNA synthetase. We'll check if amino is a perfect pair, if a match is them together. Sure. To find the net charge for all these steps, identify the ionizable groups, determine the pK values. The essential amino acids can carry charges determined by the R group. Okay. The essential amino acids can carry charges determined by the ionization of their functional groups in response to the pH of their environment. Ionization of the functional groups. Yeah. The net charge amino acid is summation of the ionizable groups, such as the carboxyl, the amino group, carboxyl group, and the R group. A amino acid is a building block of proteins. The molecular can form a peptide. The peptide bond is formed between the amino nitrogen of the one amino acid, that's as a nucleophile, and the carbonyl carbon of the other amino acids being added, and that acts as the electrophile. Will be possible through resonance bonding. Resonance. There we go. A condensation reaction, which are filled together by peptide bonds. The essential amino acids can carry charges determined by the ionization of their ionizable groups such as the carbonyl amino group and the R side chain, which is determined by their which is determined by their pH environment, which is determined by the response to the pH of their environment. Yeah. Sure. Celebration context of proteins is celebrated in the context of proteins is determined by the ionic bonds due to the ionic bonds due to the opposite charges of the amino acids. Yeah, ionic interaction. Okay, that's pretty good. The isoelectric point refers to an amino acid's ability during gel electrophoresis to not migrate due to assigning the exact pH at which the net charge is 0. Right. Which it carries no charge. In which it carries no net charge. There's nothing on here, so let's suspend the card. There's nothing in here either. Let's suspend the card. Polypeptides have a amino termini and a amino and carboxyl termini. Oh, N and C termini only at the first and last residues. Residues in between have peptide bonds which are amide groups, not ionizable. The R groups. Sarcodon is always AUG, just because that's the month of my birthday. The 3 guards act like the red stop signs. You are annoying. You are annoying. You are annoying. You go away. You are annoying. Oh, UAA. Uga. Oh, wait. UG is start. Stop is UAA. Oh, UAA. UHG. UAG. Yeah. UAG. No. What's the last one? Oh my god, why is it not coming to me? Start is always AUG. Stop is UAA. Oh, wag. 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 Agu. Wag. Ag. Wag. 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 Agu. UAA. UAG. AGU. UAA. UAG. UG. Oh, it's Ooga. Shoot. Oh, they all start with U. You. What is it? You. Oh, you are gross. You are annoying. You are gross. You go away. You go away. You are gross. You are gross. You are gross. Ooga. I can't remember. What? Ooga. But you are gross. You are gross. You are gross. You choose a positively charged amino acid like histidine, lysine, lysine. Oh wait, histidine, lysine, arginine. Histidine, lysine, arginine. AUG, AUG, UAA, UAG, UGA. So yeah, UAA, UAG, UGA. A protein, amino acid, an amino acid is the building block of protein, can form a polypeptide, a peptide. Charges determined by the R groups. Oh man, that was completely wrong. AUG, UAA, UAG, UGA. Gary charges determined by the ionization of their functional groups, which is determined by the pH of their environment. Yeah, that's fine. Carry charge is determined by the ionization of the functional groups, which is determined by the response of the pH in their environment. Let's go. And I have to do high yield. Should we study high yield as well? Well, I kind of want to look at them though. So let's look at all of them real quick. Amino group NH3. Yeah. Salt bridge. Amino backbone is 8. Carboxyl COO negative. COH. It's NH3, it should be COH. Hydrogens. That's fine. I can't finish this one right now. I want to move on though. I guess I should until it's fully there, huh? Sure. All right, let's sure. I know we shouldn't, but let's take a 10-minute right now. I need just a little bit of time to clear my head. Let's take a 10-minute real quick. I need to clear my head. Also use the restroom. We should work out after this. Anyways, we're back. Yeah, let's do this one too. Might as well, since we finish with it, and then I'll do it tomorrow morning, right? %. 50%. If the pH is below the pKa, we're going to protonate. If the pH is above the pKa, we're going to deprotonate. Yeah. Maybe we can do that one again, I guess. The carboxylic acid backbone group is going to be 2 to 3. Oh, 3. Okay, 3. I mean, I guess that's fine. That's good, I think. Individual amino acids undergo a condensation reaction and physical properties which are held together by something called the peptide bond. Yeah, condensation reaction. That is very good. Yeah. Maybe the common acid targets for phosphorylation are the amino acids cysteine, not C with a C, cystine, 39 and tyrosine. Wait. Oh, serine, not cystine. Ooh, cystine. I said cystine. What am I talking about? Serine. Yeah, serine. A blank in the context of proteins. What are we talking about here? Salt bridge. Salt bridge. Again. Amino backbone group is 8. Carboxylic group COOH. pKa values correspond to which 50% of the hydrogens are still sticking around. Yeah. If the pH drops, if the pH is below the pKa, we're going to protonate. If the pH is higher than the pKa, we are going to deprotonate. Undergo condensation reaction and use to form by something called the peptide bond, which is a covalent bond. Peptide bond between the carboxyl group of the terminal to the end. Yeah, okay, that's fine, that's good. Aspartic glutamic acid or 4. You're missing the carbon. Who's missing the carbon? Wait. R group, hydrogen group, yeah. Hydrogen group. pH is equal to the pKa. If the pH, you remove the proton. If the pH is less than the pKa, you burn it. The pKa of a specific acidic proton is the pH value. Oh yeah, okay. pKa. Common amino acid targets for serine, 309, and tyrosine. Serine, 309. Histidine group is 6. pKa values. Arginine is 12. R group 11, close to 11. It's fine. Amino group NH plus 50%. Serine, 309, and tyrosine. Salt bridge. Stabilizes tertiary structures, can be broken by heat. pKa. 3. Condensation reaction. Carboxyl group, COH. Carboxylic acid. Amino backbone 8. Hydrogen group H. Hydrogens 6. 309. Tyrosine. Peptide bond 4. Serine 11. pKa values. pKa 12. 50%. R group 9. Amino group. Salt bridge. Stabilized tertiary structures can be broken by heat. That's pretty easy to hack. That's fine. Yeah, buddy. We're already at 219 cards. Let's go. Do it every day. Do it every day. All right, finally, man. Finally, buddy. We can hit the next section. All right, let's try and do 3 sections today. It's 3:30. We got till 8. So we got like 4 hours, 30 minutes. I think we can do it. Maybe. Now we can hit 2 sections, and I'll still be pretty happy. All right, next one. Right here. Let's go. Let's take 12. This is a secret. We go over the secret.
take you?
No, Mom.
Okay. ¿Quieres comer algo?
En como 2 horas.
Okay.
Pues gracias. Yeah, see, so this was already yeah. This is at 50%. 50% of hydrogens are still around. Yeah, so it should be like this. It's already.
Angel, where's David? Can't find him.
Blue is the most basic, then green, then yellow, then orange, then red, I guess. Yellow has the most. Most acidic, the most basic. Yeah, that makes sense. I'm trying to get to the. Positive side. They're trying to get to the negative side. That's an amino confirmation. Yeah, that makes sense. Specific DNA sequence. I gotta pee.
Sorry about that. Sorry about that. Sorry about that. Look at that. Such a clean Anki deck. It's clean today. Make sure it's clean every single day. We have to add more today. Oh, by the way, what do you guys see? Oh my god, you guys can't even see what I'm seeing. Whoopsie daisy. My bad. There you go. There we go. Okay.
Hmm. plus polar. Here's a 2017. Mm. Right.
with a black pen on a piece of paper and then accidentally smudge the paper with water, what do you remember seeing? Well, what happens is that you might see the black ink start to smudge and start to see some colors that aren't black at all, maybe some dark blues and some dark purple. But why is this? This is because, have you ever scribbled something down with a black pen on a piece of paper and then accidentally smudged? Ever scribbled something down with a black pen on a piece of paper and then accidentally smudged the paper with water? What do you remember seeing? Well, what happens is that you might see the black ink start to smudge and start to see some colors that aren't black at all, maybe some dark blues and some dark purples. But why is this? This is because black dye is actually made out of a bunch of different other dyes and different, and what you've just witnessed is a basic example of paper chromatography. Chromatography involves taking some kind of mixture and using either solid or liquid to separate it out into its different parts. There are many different kinds of chromatography, but they all rely on having a mobile phase and a stationary phase. Let's go over how paper chromatography works, since this is the simplest kind. In paper chromatography, the stationary phase is the paper. So here's your piece of paper. You can draw a little line at the bottom and draw a spot for where you're putting on your dot of your sample. Next, you'll want to prep a beaker, or actually any kind of container will do. But in this, you'll be putting in your mobile phase. And your mobile phase can be some kind of solvent. It could be water, or it could be any organic solvent you want. Now that you have this, you pour in a small amount of solvent. Again, not too much, because you don't want this to already be above the level of your spot, or else it'll just all bleed. And now when you put in your paper into this container, what you'll get is something that looks like this, with the spot being around here. And what you'll observe over time is that through capillary action, this pink solvent will travel up the piece of paper. And as it does that, it'll actually take some of the dyes from that green spot with it. And let's see what happens at a few different time points. At the first time point, you might see that it's separated into two spots. This implies that it's composed of two different components. However, if this were a very complex mixture, you could even see 5, 6, or a lot of other spots. If you wait even longer, this is what you'll see next. You'll see that the spots will continue traveling even farther up the plate, and the separation between them, that distance will increase even more. So ultimately, what you've shown here is that whatever was in the green spot originally wasn't just one compound, it was two compounds. And why do they separate in this manner? Well, the blue spot traveled farther. That means that it was pretty attracted to that pink solvent that was traveling along, whereas the yellow spot didn't move quite as much, which means it was more attracted to the paper, or the stationary phase. This competition became even more. So ultimately, what you've shown here, very complex mixture, pink solvent will travel up the piece of paper. And as it does that, it'll actually take some of the dyes from that green spot with it. And let's see what happens at a few different time points. At the first time point, you might see that it's separated into two spots. This implies that it's composed of two different components. However, if this were a very complex mixture, you could even see 5, 6, or a lot of other spots. If you wait even longer, this is what you'll see next. You'll see that the spots will continue traveling even farther up the plate, and the separation between them, that distance will increase even more. So ultimately, what you've shown here is that whatever was in the green spot originally wasn't just one compound, it was two compounds. And why do they separate in this manner? Well, the blue spot traveled farther. That means that it was pretty attracted to that pink solvent that was traveling along, whereas the yellow spot didn't move quite as much, which means it was more attracted to the paper, or the stationary phase. This competition between the stationary phase and the mobile phase, pulling out the components, is what drives the separation that occurs in all different kinds of chromatography. So let's try to lay this information out in a table. We've talked about how for paper chromatography, the stationary phase is a solid, the mobile phase is some kind of solvent, so a liquid, and they're separating it based on polarity, meaning how attracted it is to the paper versus the solvent, depending on its chemical properties. The next kind of chromatography that's almost identical to paper chromatography is known as thin layer chromatography, or TLC for short. You'll see that all the spots in this table are pretty much the same. The main difference is that instead of having a piece of paper, you have a glass slide that is coated with a layer of silica gel. This is a great preparative tool that's commonly used in the organic chemistry lab. To remind you that these two are related, what I've drawn here is a little beaker with a small either plate or piece of paper inside, and the arrow shows that the solvent is traveling up the plate through capillary action. The next kind of chromatography we'll be going over are column chromatography. And in this case, you have a column that I've drawn here on the left, and you fill it with some kind of packing material and dump in some solvent as well. You can load your sample that you want to separate out, and what you'll find is that as you keep dumping in more solvent, this can separate into bands that represent different compounds, and they will travel down the column. So in basic column chromatography, you're usually using something like silica gel as your stationary phase. Your mobile phase is typically an organic solvent, and again, you're separating based on polarity. In size exchange chromatography, your stationary phase is composed of beads. However, and because of that, with size exchange chromatography, these beads completely fill the column, and tiny compounds can get through that center of the hole, like so. But really big columns kind of have to go around and go between the beads. So what happens here is that really small compounds travel pretty far, pretty fast, or actually have some holes in the middle. And because of that, with size exchange chromatography, these beads completely fill the column, and tiny compounds can get through that center of the hole, like so. But really big columns kind of have to go around and go between the beads. So what happens here is that really small compounds travel pretty far, pretty fast, whereas large compounds take a longer time to come out the bottom. In ion exchange chromatography, the beads that are filling this column have some kind of group on them that is charged. Compounds that have the same charge will be repelled by the column, meaning they'll travel pretty quickly. But compounds that have an opposite charge will bind tightly to the column and will be more reluctant to come out since they're so attracted to the stationary phase. Affinity chromatography is also pretty similar, but this usually relies upon very specific interactions, such as between an enzyme and a substrate, and really relies on this binding affinity. Things that will bind tightly to the enzyme will probably just be primarily the substrate, and everything else will just get washed right off the column. Later on, what you can do is wash out the compound of interest that was previously bound to the column, using something that molecule is even more attracted to. With HPLC, stands for High Performance Liquid Chromatography, formerly known as High Pressure Liquid Chromatography. This is essentially the same as the basic column chromatography that you see there in yellow. However, with HPLC, it's a more advanced technique in that you're working with very, very small quantities, and the detector in the machine is much more sensitive. The last kind of chromatography is gas chromatography. Now, this looks pretty different compared to the others, and in this case, your stationary phase is a liquid, while your mobile phase is some kind of carrier gas that's passing over the liquid. So what happens is you inject your sample, and it travels in a coiled tube into that box known as the gas chromatograph. That's the fancy name for the equipment used to run gas chromatography. Inside the chromatograph is a heated chamber through which an inert gas flows. Here, the sample vaporizes and enters the gas flow onto the column. The things that are the most volatile, meaning have a lower boiling point, are able to travel faster, whereas things with a higher boiling point take longer to come out. And so this is a separation method that's great when you have differences in boiling point. So I've gone over all these different kinds of chromatography, but you could certainly go into each of these in much more detail.
In a previous video, we talked about thin layer chromatography, and it was a technique used to figure out how many things you have in a sample, or maybe say the relative properties, say the relative polarity of the things that you have in the sample. And so what you do is you put a sample on typically a silica gel, which is I gotta be. the stationary phase. And then you put a mobile phase down here, which in this case might be less polar. And then it's going to move. In a previous video, we talked about air chromatography. And it was a technique used to figure out how many things you have in a sample, or maybe say the relative properties, say the relative polarity of the things that you have in the sample. And so what you do is you put a sample on typically a silica gel, which is the stationary phase. And then you put a mobile phase down here, which in this case might be less polar. And then it's going to move its way up the silica gel. And as it does, you can imagine it's going to interact with the original sample. And so parts of the original sample are going to move up with your mobile phase. And different parts are going to be attracted to that mobile phase and not attracted to the silica gel to different degrees. You can imagine if there's a part of your original sample that is more polar, then it's going to be harder to move because it's going to be attracted to the stationary phase and less attracted to the mobile phase. And so it's going to move less. So this might be the more polar part of your sample as it moves from its original location. And the part that's less polar, well, it's not going to be as attracted to the stationary phase. And so it's going to be more, and it's going to be more dissolvable in the less polar mobile phase. And so it will go further. So this will be the less polar part of your original sample. And so you can see that separation, and you can come up with other insights. We talked about that in that other video. In this video, I'm going to introduce you to a very, very, very similar idea. It's just things are moving in a different direction. And that is the notion of column chromatography. What you do in column chromatography, just like thin layer chromatography, is let's say you have some type of vial, some type of column, I guess I could say, and you'll typically see it with a little cap drawn down here because you might want to see what comes out through the bottom. What you do is you fill it with the stationary phase, which once again is oftentimes silica gel. So this is stationary phase. And if it's silica gel, in this case, silica gel, it doesn't have to be silica gel, that's pretty common. This is going to be very polar. So let me write this, very polar. And then you put some of your sample at the top here. So that's your original sample, you put it at the top. And then you have some mobile phase, the solvent that you're going to put on top of that. So you're gonna do something like that. And what do you think is going to happen? Well, your mobile phase is going to start moving its way down through your stationary phase. It's going to interact with your sample. Now, what's going to happen to the more polar components of your sample? Well, the more polar components of your sample are going to be more attracted to the stationary phase, less attracted to the mobile phase. So they're going to move less. So the more polar parts of your sample might only go maybe that far, while the less polar parts of your sample, they'll be less attracted to your stationary phase, and they'll move with your mobile phase more. And so they might move down over there. And so the big takeaway, the difference between the two is just the direction you're moving in. In thin layer chromatography, your more polar thing is the lower dot, while in column chromatography, your more polar thing is the upper layer right over here, this purple area right here. And of course, all of that depends on the polarity of your stationary phase and the relative polarity of your mobile phase. But what I just showed you is a typical situation. So keep in mind, whether you're looking at thin layer chromatography or column chromatography, which to pay attention to the direction.
Sure. We'll take 10-minute here. I'll work out on the next one. How many courses will you study? How many courses? I don't know. I don't know what she means. I'm studying the whole thing. Like, I'm studying the whole thing from start to finish in 3 months. Oh. Intermolecular forces.
Hey guys, sorry about that. I'm back. We're back. Sorry about that. I had to make yes, a some food. Okay, Mom. Thank you. Yes, sir. Let's go. Let's go. I'm talking about. What I'm talking about. Food is the best, man.
And it with a chocolate. Let's do the red one. Oh no, let's do the blue one. Let's try the red one actually. Hopefully I can eat some chocolate during the I can eat some chocolate during the exam. Be kind of cool. And during the break. Yeah. Oh wait, go back. Measuring intensity. I'm gonna say boiling. Let's see here. I think it's the one that actually has more of them, though. This is literally just NHKC. The other one's gonna be DDEK. Basic. Basic. Arginine. We have, N, K. F doesn't really matter. R again, G, and C. And then N, E. E doesn't matter. T. T is 309. Might do T. V, N. of DC, the greatest isoelectric point. The more basic one, right? The most basic one here is going to be RHKRR. RHKRR. Oh my god, let's go, dude. Really? I'm not too worried about this section. I don't really think it's going to be on there much, so we're just going to skip it out for now. Yeah. Basically, metals have higher P isoelectric values. Which of the following peptides is likely to travel the farthest towards a negative electrode? Um, HK. Oh man, DDEK. C, super negative. R, K, R, and then E, F, phenylalanine. Phenylalanine nonpolar. Wow, we really only have E in that. Towards negative electrode? I'm gonna say H and K, so it's gonna be A. Oh man. Then it's gonna be I mean this one has more positive. Oh okay. Yeah, almost all of them are positive here. Okay. think it's the polarities, right? Yeah. Based on size. Infiltration. To react. Yes. Components. I think it's a stationary phase, right? I don't know. Can you example to the column? Yeah, okay. Proliferating cell nucleation is a homotrimeric protein that functions as a processivity factor for polymerases during DNA replication. Figure shows native gel electrolysis of all type of making pCNA proteins. For the lower band, in the case of maybe this one. I guess it's in the trimeric state. I'm not too sure. Okay. The protein one is incubated in the presence of PTP before the version was turned on. To the form does not represent the result. They do. There's proteins in the halo. Oh, I guess what is it? Homodimer of 233 kilodalton subunit 13 out. Further. Oh. That's false because they do. Gotcha. Microvesicle and apoptotic. Something very fast. So we're looking at 164. Yeah. I guess. That's fine. Enzyme structure and function, enzyme kinematics. Enzyme kinetics. I keep saying kinematic. Enzyme kinetics. DNA replication, transcription, and translation. Nothing on that. Gene control. Okay. Genetic mutations. Sure. Gotcha. Energy relation reaction. Exergonic with a negative 3 gives energy state needs energy to proceed. Reactant molecules. Reaction takes place. Yeah, okay. Ah. Okay. Okay. Oh, okay. Gotcha. Gives me energy or reaction process. Hmm. Oh, wow.
And
Whoa, you're kind of loud, buddy.
enzymes and how they're critically important pieces of cellular machinery.
You're too fast.
But first, let's review the idea that biochemical reactions happen in the body all the time. Almost every cellular process involves a biochemical reaction.
Oh. Fighting the flu with oseltamivir. Oseltamivir? Oh, did I miss this one? Oh, no, that's something else. I think we're okay.
Reaction at one.
All right, let's take a 10-minute. We might go a little bit more today, to be honest, because I really want to try to get through lesson 4. You know? Because the rest of the stuff is like kind of a little bit more my style. So I think, I think we'll just try to keep going, I guess. I don't know. Maybe for like an hour or two. Maybe an hour. We'll go an extra hour, so we'll go 3 more hours. But for now, let's take a 10-minute. Oh, actually, what's the video at? Because I'm gonna have to do continuation video. Maybe. Yeah, I'll do a continuation video. I'll be like for like an hour. But at least it'll be something, right? let's take a 15-minute after this and exercise. I think it's important that we exercise. Because I'm feeling pretty good. Anyways, let's get on it.
Is actually just a series of different biochemical reactions in carbon metabolism.
Hold on, buddy. Slow down.
So today I want to talk to you about enzymes and how they're critically important pieces of cellular machinery. But first, let's review the idea that biochemical reactions happen in the body all the time. Biochemical reaction at one point or another. The TCA cycle is actually just a series of different biochemical reactions in carbon metabolism. DNA replication, which needs to happen before a cell can go through mitosis, is also just a series of reactions. And this also applies to the expression of genes, going from DNA to RNA to protein. And we need enzymes because enzymes make all of these reactions go much faster. And let's look at this idea of make all of these reactions go much faster. And let's look at this idea a little more deeply and how a reaction will go on differently when it has an enzyme versus not having one at all. So you may be familiar with the reaction where water and carbon dioxide.
Go away. Go away. Go away.
Can combine to form carbonic acid. And this is a reversible reaction, so it can go backwards and forwards. Now, when people make soda or any carbonated beverage, they'll start by pumping that soda can full of CO2. And while some of that CO2 will dissolve in the water in the can, the soda making companies are able to get a lot more CO2 in the water by using this reaction. The abundant CO2 will react with the water to form some carbonic acid in the can. And when you go to open the can, you'll hear a pop sound, which is really just a bunch of CO2 escaping. But after that, the soda will start to fizz really slowly. And what's happening here is the carbonic acid that was made before is slowly dissociating back to carbon dioxide and water as CO2 escapes. And that extra CO2 that's being made will come out of the soda solution, and you'll see it as little bubbles floating around. But what happens if we then take this person over here and he'll pick up a can of soda and take a drink? That person might notice the soda will start fizzing a lot more once it hits his or her tongue. And this is because humans have an enzyme in their blood and saliva called carbonic anhydrase. And this makes the carbonic acid turn into carbon dioxide and water much more quickly. So more carbonic acid turn into carbon dioxide and water anhydrase. And this makes the carbonic acid turn into carbon dioxide and water much more quickly. So more CO2 will come out of the can and it'll fizz more. And this is just one of the many examples of how enzymes make reactions go faster. So how exactly do the enzymes make the reactions go faster, though? Well, they use a bunch of different catalytic strategies to push reactions along a little more quickly. And I'm going to talk about a few of those strategies just to give you an idea of what enzymes are doing. So first I'll mention acid-base catalysis, which happens when enzymes act like either acids or bases. Now remember that acids and bases are proton donors and acceptors. And if you look at this type of a reaction, which if you remember from organic chemistry is a keto-enol tautomerization reaction.
Okay.
reaction, we have a proton moving from a carbon atom to an oxygen atom.
Proton moving from the carbon atom to an oxygen atom.
And since acids and bases are pretty good proton carriers, they could both help with this reaction and make it go a little more quickly by helping to move that proton around, instead of this molecule doing it by itself. Our next catalytic strategy is covalent catalysis, which happens when enzymes form a covalent bond with another molecule, usually their target molecule. Remember that covalent bonds involve two molecules sharing electrons. And looking at this reaction here, we have a decarboxylation. Reaction
Decarboxylation.
going on, which, if you remember from organic chemistry, is when a carboxy or CO2 group is being taken off a molecule. And if you remember, these reactions usually have a lot of electrons moving around. So if we had a covalently bound enzyme that could hold on to some electrons, be an electron carrier, or what some people like to call an electron sink, then that would definitely help this type of reaction move a little more quickly. Next, we have electrostatic catalysis. Now, if you remember, DNA is a very negatively charged polymer because of all the negatively charged phosphate groups that we find in DNA.
Oh, it was bad, but whatever.
So if an enzyme had a metal cation on it, like magnesium, we could use it to stabilize the negative charge found in DNA and make it a little easier to work with. And DNA polymerase, which is the enzyme that allows DNA replication to occur, does exactly this. And in order for it to help with DNA replication, it needs to find a way to counteract all of the negative charge
Right.
on DNA. And magnesium ions totally come in handy there. So the last catalytic strategy I want to mention is a little more general, and it has to do with proximity and orientation effects. Remember that in order for two molecules to react with each other, which is usually what enzymes help out with, they need to physically collide at some point. If we have molecule A and molecule B, they'll only react once they crash into each other. And a lot of enzymes are able to bring two molecules close together so that these types of collisions happen more often, making the two molecules react more quickly. Also remember that the orientation of the two colliding molecules in space is also really important. If molecule A and molecule B collide, but one of them is upside down or not in the correct position, then the collision may not result in a successful reaction. So enzymes also make sure that the two molecules will collide in the right orientation. And all of this increases the frequency of collision in general, but also helps to make sure that those collisions are successful and result in a reaction. So what did we learn? Well, first we learned that the role enzymes play is to make biochemical reactions happen more quickly. And the next thing we talked about were 4 of the many different catalytic strategies that enzymes can use. We talked about acid-base catalysis, which helps with proton transfer. We talked about
covalence, electrostatic, proximity, and orientation.
covalent catalysis, which helps with electron transfer. We mentioned electrostatic catalysis, which deals with stabilizing charge.
Isn't that another way of saying just ionic, kind of?
And finally, proximity and orientation effects, which increase the frequency of successful collisions between molecules that we want reacting together.
Great. Well done. I'm not going to get into it right now.
Today, we're going to talk about how enzymes can influence a reaction's activation energy. But first, let's review the idea that enzymes make biochemical reactions go faster. And in order to do that, they use a bunch of different catalytic strategies. Now, there are lots of different catalytic strategies that enzymes use, but a couple of the key ones are acid-base catalysis, where enzymes use their acidic or basic properties to make reactions go faster by helping it with proton transfer. There's also covalent catalysis, where enzymes covalently bind a reacting molecule to help with electron transfer. There's electrostatic catalysis, where enzymes use charged molecules or metal ions to stabilize big positive or negative charges. And we also have proximity and orientation effects, where enzymes make collisions between reacting molecules happen a little more often. So what effect do these catalytic strategies actually have on a reaction? Well, let's look at a sample reaction where we're having molecule A being converted to molecule B. Now, we can look at the process of this reaction using something called a reaction coordinate diagram. And here, we'll plot the energy state of our molecules against the progress of the reaction. So essentially, using this graph, we'll follow the energy level of molecule A as it's converted to molecule B. Remember, the molecule's energy level is related to its stability, and something that is a lower energy state is more stable, and for something to transform to a more unstable form, it needs an input of energy to get there. Is related to it's converted to molecule B. Remember, the molecule's energy level is related to its stability.
Oh, okay.
And something that is a lower energy state is more stable, and for something to transform to a more unstable form, it needs an input of energy to get there. So looking at this graph, you'll notice that the energy of molecule A will rise up pretty high and then drop all the way down to the energy of molecule B. And we can actually define a couple of values from this graph. The transition state of a reaction, which is represented by this double dagger symbol, is the highest energy point on the path from A to B, and it's where you'll find the most instability throughout the entire reaction.
Right. Gotcha.
Now, the difference between the energy level where we start and the top of our graph at our transition
Okay, where we start to the top is keeps free energy state.
state is what we call the delta G double dagger, or the free energy of activation.
Free energy activation. I don't really have any space.
And this is the amount of energy that A needs to have in order to break the reaction barrier to ultimately get to point B. You'll also notice that there is a difference in energy between point A and point B. And we call this the standard free energy change for the entire reaction. And it represents the net change in energy levels between our reactant and our product.
Oh.
Product, and it's also the energy that is released into the environment once the reaction is over. Reactions you typically look at will have their products at a lower energy state than their reactants, since that makes the reaction spontaneous. Now, it's important to recognize that it is the free energy of activation energy value, which is the difference between point A and the transition state, that usually determines how quickly a reaction will go. And usually this energy value is much higher than the free energy change for the reaction, which is why enzymes state that usually determines how quickly a reaction will go. And usually this energy value is much higher than the free energy change for the reaction, which is why enzymes speed up a reaction by lowering a reaction's activation after the reaction is over. Reactions you typically look at will have their products at a lower energy state than their reactants, since that makes the reaction spontaneous.
Okay.
Now, it's important to recognize that it is the free energy of activation energy value, which is the difference between point A and the transition state, that usually determines how quickly a reaction will go.
Mm-hmm.
And usually this energy value is much higher than the free energy change for the reaction.
Free energy change and the free energy change for the reaction. And the free energy change of the reaction, it's much higher than the free energy. Okay, yeah, this line is higher than this line. Yeah, that makes sense.
Which is why enzymes speed up a reaction by lowering a reaction's activation energy.
So if we lower the activation energy.
Now, I want to quickly
The activation energy is where?
point out that you may see delta G double dagger written out as EA in some textbooks, and you may see the standard free energy change for the reaction written out as E reaction.
Buddy, what the heck? What the heck, buddy?
And I'm just letting you know that you might see both sets of terms used from time to time. Now, let's look at an
Free energy vacuum. This guy.
an analogy to get a closer look at how this all works.
E what? What is
Now
it?
it is E reaction.
E reaction.
And I'm just letting you know that you might see both sets of terms used from time to time.
Thank you.
Now, let's look at an analogy to get a closer look at how this all works. And let's say there's a giant hill that you're
Oh, by the way, am I sharing? Yeah, I'm sharing.
trying to climb. And it's a pretty steep hill that goes up really high, but you need to get to the other side of the hill. Now, this would be a pretty scary thing on its own, since you would need to go all the way up and then all the way down the mountain to get to the finish line. But if I were to give you a shovel, then now you could dig your way through the mountain and not have to climb up so high. In this example, the shovel represents an enzyme and the hill represents the activation energy barrier that prevents you from getting to start to finish. But if I were to give you a shovel, then now you could dig your way through the mountain and not have to climb up so high. In this example, the shovel represents an enzyme and the hill represents the activation energy barrier that prevents you from getting to start to finish. By using the shovel, you're able to lower the height of the hill you have to climb. But in both cases, it's important to recognize that you still started and finished at the same points. So let's go back to our example from before with our reaction coordinate diagram. But now, let's say that the reaction has a...
Wait, walk sign is on. Wait, walk sign is on.
catalyst.
Let's use a different color now.
So with the catalyst, the activation energy barrier that molecule A
Uncatalyzed,
has to overcome in order to get to point B is much smaller. And this will mean that your reaction will have a transition state with a much lower energy, meaning that it's more...
Wait. Hold the phone. Obama. He gave me a phone. Obama phone.
More stable with the enzyme, and also that the reaction as a whole will have a much lower activation energy. Now, it's really important to recognize that, like our example where you're trying to climb the hill, the enzyme will not be changing the starting and ending point.
Starting and ending points don't change.
Points of the reaction. It doesn't change molecule A or molecule B. Your starting and ending points are always the same, and the only thing that changes is the path that you take to get from A to B. Now, since our starting and ending points aren't changing, it follows that the enzymes are not used up when they catalyze a reaction. And there is no permanent change to the enzyme following. reaction. So what did we learn? Well, first we learned that end action, it doesn't change molecule A or molecule B. Your starting and ending points are always the same, and the only thing that changes is the path that you take to get from A to B. Now, since our starting and ending points aren't changing, it follows that the enzymes are not used up when they catalyze a reaction, and there is no permanent change to the enzyme following a reaction. So what did we learn? Well, first we learned that enzymes work by lowering the free energy of activation of a reaction, making it much easier for the reactants to transition and form products. And we also learned that the free energy of the reaction doesn't really change when you use an enzyme and when you don't. Second, we learned that despite the change in pathway to get from A to B, the reactants and products do not change when using an enzyme versus when not using an enzyme. And finally, we learned that enzymes are not consumed when they catalyze a reaction, and the same enzyme can catalyze reactions over and over again.
Yes, sir. Okay. Let's keep going.
So today I'm going to talk to you about the induced fit model of enzyme catalysis and how this concept can tell us a lot about how enzymes work. But before we do that, let's review the idea that enzymes make reactions go faster. And when you look at a reaction on a reaction coordinate diagram, you'd see that the catalyzed reaction would have a much smaller activation energy than the uncatalyzed one. Also remember that because of this, the energy of the catalyzed reaction's transition state is far lower than the energy of the uncatalyzed reaction.
Hold on, buddy.
One. Also remember that because of this, the energy of the catalyzed reaction's transition state is far lower than the energy of the uncatalyzed reaction's transition state. So what do enzymes look like? Well, most enzymes are proteins, or at least partially made up of proteins. And substrates are any molecule that an enzyme will act on. And often these substrates are the substrate. Most enzymes are proteins, or at least partially made up of protein. And substrates are any molecule that an enzyme will act on. And often, so what do enzymes look like? Well, most enzymes are proteins, or at least partially made up of protein. And substrates are any molecule that an enzyme will act on.
Any molecule.
And often, these substrates are the reactants that the enzyme will molecule that an enzyme will act on. And often these substrates are the reactants that the enzyme will ultimately help turn into products through a reaction. Now, enzymes also have what is called the active site, which is the location on the enzyme where substrates bind. And that's where the reaction ultimately happens. And it's important to recognize that every enzyme site, which is the location on the enzyme where substrates bind. And that's where the
Why do I need substrate 2? Substrate benefits.
reaction ultimately happens. And it's important to recognize that every enzyme has a unique active site that will only bind to certain substrates. And just to clarify, I've referred to the active site here as both of the notches found on the enzyme. And just to clarify, I've referred to the active site here as both of the notches.
Oh, so they're both active sites. Active sites.
Found on the enzyme, and not the space in between them.
For what?
Just to clarify, I've referred to the active site here as both of the notches found on the
Both notches.
enzyme, and not the space in between them. So here, of the two substrates I've drawn, the enzyme will only be able to bind to substrate 1, since they fit together like puzzle pieces, whereas the shape of substrate 2 isn't going to fit nicely in the enzyme's active site. Now, since enzymes have unique active sites, we say that enzymes are specific to certain substrates, and by extension, certain reactions. But let's dive a little deeper into what happens when enzymes and substrates bind each other, and how that binding pattern changes as a reaction progresses. So first, you'll have your enzyme here and your substrate over here, and I'm just going to label this with a number 1, since it'll be the first thing that happens in the sequence of events to come. And at this stage, nothing has happened yet, and the enzyme and the substrate have yet to come in contact. So next what will happen is the enzyme will bind the substrate, but this binding won't be perfect. So I'll call this initial binding, which is stage 2 of the process. And what that means is that the forces holding these two together are strong, but they're not at their maximum strength just yet. And enzymes and substrates don't actually fit together quite like puzzle pieces. And they actually work a little bit more like two pieces of clay that will both mold together so that the fit is much tighter. So in our next step, this is exactly what happens. The enzyme and the substrate will both change shape a little bit and bind to each other really strongly. And we call this the induced fit because both the enzyme and the substrate have changed their shape a little bit so that they bind together really tightly. And it's at this point where the reaction that the enzyme is catalyzing is at full force, and this would be stage 3. So our next stage occurs after the reaction is completed, and the binding becomes similar to what it was in stage 2. But the difference here is that and it's at this point where the reaction that the enzyme is catalyzing is about to creep a little bit and bind to each other really strongly. And we call this the induced fit because both the enzyme and the substrate have changed their shape a little bit so that they bind together really tightly. And it's at this point where the reaction that the enzyme is catalyzing is at full force, and this would be stage 3. So our next stage occurs after the reaction is completed, and the binding becomes similar to what it was in stage 2. But the difference here is that there's something different about the substrate. So in this reaction, the enzyme is cutting our substrate into 2 parts. So now the 2 parts have become separate, and that the enzyme is catalyzing is at full force, and this would be stage 3. So our next stage occurs after the reaction is completed, and the binding becomes similar to what it was in stage 2. But the difference here is that there's something different about the substrate. So in this reaction, the enzyme is cutting our substrate into 2 parts. So now the 2 parts have become separated. And this would occur after the reaction is finished, and we'll call this stage 4. Now, in our next and last stage, the products of the reaction have been released from the enzyme, and our enzyme is back in the same state that it was in stage 1, and we'll call this stage 5. Now let's look at this from a slightly different angle. I'm going to label the enzyme as E, the substrate as S, and our 2 products as P1 and P2. And they're going to represent this series of events as different steps in a sequence of reactions. So first we'll have E and S separate, and this is stage 1. And
Enzyme E. substrate S.
And next, E and S will bind to each other to form an enzyme substrate complex, which called ES and corresponds to stage 2 from before. Now, what's really interesting is that in the next step, where we had the induced fit of stage 3, we're actually at the transition state of the entire reaction. And this is the same as that really high energy point that we saw at the beginning of this video. And it's at the point of the transition state where our enzyme is most tightly bound to its substrate. Now, I've written the substrate out here with the letter X because at the reaction's transition state, our substrate isn't quite our reactant and it isn't quite our product substrate. Now, I've written the substrate out here with the letter X because at the reaction's transition state, our substrate isn't quite our reactant and it isn't quite our product either. It's somewhere in between. So that's why I've written it out as X instead of S. And I've also written this double dagger symbol, which is just a universal symbol for transition states. Now, in our next stage, which is after the reaction has occurred, since it exists after the transition state, we have the enzyme bound to the two products P1 and P2. And this was stage 4 from before. And then finally, in our last stage, stage 5, we have our enzyme, which is now separated from our two products P1 and P2. Now, the big takeaway from all this is that binding between enzyme and substrate is strongest at the reaction's transition state. And this is because
it happens at the induced fit.
the enzyme and the substrate have molded together. Binding between enzyme and substrate is strongest at the reaction's transition state. And this is because the enzyme and the substrate have induced fit.
Yeah. Coming. I'm coming. All right, thank you. Let's go. We got food. Yeah. Got food. Yeah, buddy. I'm so happy, aren't you guys so happy? I'm so happy. Look at us. Just a couple of old students trying to learn all about this. Enzymes and transition states. Activation energies. Anyways, let's continue. Oh boy, so good.
Now, some enzymes will actually bind more than one substrate. And if we look at a reaction that might be familiar, which is lactic acid,
Yeah, buddy. Some enzymes bind more than one substrate. Pyruvate. NADH. Lactic acid.
lactic acid fermentation, we can see that our enzyme lactate dehydrogenase will have space to bind two different
activation sites.
substrates in this.
Two different activation sites. So when you refer to that on those, it's just one active site. It has two different active sites. So we're going to produce four substrates. We're going to produce four different substrates.
Reaction, one space being for NADH and the other being for pyruvate. So enzymes don't necessarily bind just one substrate. Now, sometimes things will bind to enzymes at places other than their active sites, and we call this allosteric binding. So if we have an enzyme here with its active site, a regulating molecule, like an inhibitor, may bind the enzyme at a different location than the active site, won't necessarily bind just one substrate. Now, sometimes things will bind to enzymes at places other than their active sites, and we call this allosteric binding. So if we have an enzyme here with its active site, a regulating molecule, like an inhibitor, may bind the enzyme at a different location than the enzyme's active site. Now, when something binds to an enzyme like this, it usually has the effect of changing the shape of an enzyme in some way to affect its ability to catalyze reactions. So in this case, when an inhibitor binds the enzyme, it might change the shape of the active site, thereby inhibiting the enzyme as it's no longer able to bind its intended substrate, so they don't quite fit together anymore. So while enzymes bind reactive groups at their active sites, they can also bind regulators at their allosteric sites, and allosteric sites just refer to any binding site outside of the active site. And remember, allosterically binding molecules can either be activators or inhibitors, any regulating molecule. So what did we learn? Well, first we learned its intended substrate, so they don't quite fit together anymore. So while enzymes bind reactive groups at their active sites, they can also bind regulators at their allosteric sites, and allosteric sites just refer to any binding site outside of the active site. And remember, allosterically binding molecules can either be activators or inhibitors, any regulating molecule. So what did we learn? Well, first we learned that enzymes are specific, and that they can each bind to only specific substrates to catalyze specific reactions. Next, we learned about the induced fit model, and how enzymes bind their substrates most tightly in the middle of a reaction at the reaction's transition state. And finally, we learned that enzymes have both active sites and allosteric sites, with active sites being where the reaction takes place and allosteric sites being where regulation takes place. Or to any binding site outside of these. So in this case, when an inhibitor binds the enzyme, it might change the shape of the active site that our enzyme, blackler being for pyruvate. So if we have an enzyme here with its active site, a regulating molecule, like an inhibitor, may bind the enzyme at a different location than the enzyme's active site. Now, when something binds to an enzyme like this, it usually has the effect of changing the shape of an enzyme in some way to affect its ability to catalyze reactions. So in this case, when an inhibitor binds the enzyme, it might change the shape of the active site, thereby inhibiting the enzyme as it's no longer able to bind its intended substrate, so they don't quite fit together anymore. So while admitted difference, and we call this allosteric binding, lactic acid fermentation, we can see that our enzyme lactate dehydrogenase will have space to bind two different substrates in this reaction, one space being for NADH and the other being for pyruvate. So enzymes don't necessarily bind just one substrate. Now, sometimes things will bind to enzymes at places other than their active sites, and we call this allosteric binding. So if we have an enzyme here with its active site, a regulating molecule, like an inhibitor, may bind the enzyme at a different location than the enzyme's active site. Now, when something binds to an enzyme like this, it usually has the effect of changing the shape of an enzyme in some way to affect its ability to catalyze reactions. So in this case, when an inhibitor binds the enzyme, it might change the shape of the active site, thereby inhibiting the enzyme as it's no longer able to bind its intended substrate, so they don't quite fit together anymore.
Oh.
So while enzymes bind reactive groups at their active sites, they can also bind regulators at their allosteric sites, which are able to bind its intended substrate, so they don't quite fit together anymore. So while enzymes bind reactive groups at their active sites, they can also bind regulators at their allosteric sites, which and allosteric sites just refer to any binding site outside of the active site. And remember, allosterically binding molecules can either be activators or inhibitors, any regulating molecule. So what did we learn? Well, first we learned that enzymes are specific, and that they can each bind to only specific substrates to catalyze specific reactions. Next, we learned about the induced fit model, and how enzymes bind their substrates most tightly in the middle of a reaction at the reaction's transition state. And finally, we learned that enzymes have both active sites and allosteric sites, with active sites being where the reaction takes place and allosteric sites being where regulation takes place. Today we're going to talk about cofactors and coenzymes, and how sometimes they can be essential to proper enzymatic function. But first, let's review the idea that enzymes make reactions go faster. And they do this by lowering the activation energy peak of their respective reactions. Let's also review the idea that enzymes bind their substrates at a location on the enzyme called the active site, which is where most of the reaction takes place. Now, not all enzymes are able to catalyze reactions on their own, and some need a little help. So if we have our enzyme here trying to react with our substrate over here, sometimes something called a cofactor or a coenzyme will be needed, which will also need to bind to the enzyme in order for it to function properly. And we're going to go over what coenzymes and cofactors are and exactly how they work. So first we'll talk about what a coenzyme is. Well, coenzymes are organic carrier molecules. And what I mean by organic
No.
is that they're primarily carbon-based molecules. And by carrier, I mean that coenzymes hold on to certain things for an enzyme to make the catalysis run a little more smoothly. And a great example of a coenzyme is NADH, which acts as an electron carrier. And here I've shown NADH dissociating into its oxidized form, NAD+, as well as to a hydride ion, which basically just exists as a pair of electrons that that some other molecule would be grabbing. So NAD plus can accept electrons, causing the molecule to be converted to NADH, which could then carry electrons for an enzyme. Now, if you remember the lactic acid fermentation reaction, where pyruvate is converted to lactic acid, you'd see that the enzyme catalyzing this reaction, lactate dehydrogenase, uses NADH as a coenzyme in order to transfer electrons to the pyruvate molecule in order to turn it into lactic acid. And in this sense, NADH is acting as an electron-carrying coenzyme. Another example of a coenzyme is coenzyme A, which, like NADH, acts as a carrier molecule, but instead of carrying electrons like NADH does, coenzyme A, which we sometimes call CoA, holds on to acyl or acetyl groups instead. And you'd see CoA appear quite often in metabolic reactions, where it'll carry these 2 carbon acetyl groups from one molecule to another. Now, cofactors are a little different from coenzymes. While coenzymes are only really involved in transferring different things from one molecule to another, cofactors are directly involved in the enzyme's catalytic mechanism. They don't strictly carry something like a coenzyme would, but might be stabilizing the enzyme or the substrates, or helping the reaction convert substrates from one form to another. A great example of this is with the enzyme DNA polymerase. Remember that DNA polymerase is responsible for helping out with synthesizing new DNA during DNA replication. Now, you may remember that DNA is a very negatively charged molecule because of all the negatively charged phosphate groups that you'll find around it. Well, DNA polymerase uses a magnesium ion as a cofactor, which can use its big positive charge to stabilize all that negative charge on DNA. And you can see how this is different from a coenzyme, because instead of acting as a carrier molecule, the magnesium ion cofactor is stabilizing the DNA and is more directly involved in the actual catalysis. Now, interestingly, what people normally call vitamins and minerals, like the kinds that a doctor would tell you to make sure you get enough of in your diet, are often different cofactors and coenzymes. And what's special about vitamins and minerals is that your body can't build them up from scratch, and you need to get them from your diet in order to stay healthy.
Mm-hmm.
So when we say vitamins, we typically refer to organic cofactors and coenzymes. So 2 great examples are ones we just discussed. Vitamin B3, which you may see being called niacin on a food label, is actually just a precursor for NAD. And vitamin B5 is just a precursor for coenzyme A. Minerals, on the other hand, are inorganic, meaning they aren't carbon-based. B5 is just a precursor for coenzyme A. Minerals
Gotcha. Right.
On the other hand, are inorganic, meaning they aren't carbon-based, and minerals are usually just cofactors in our body. So magnesium would be a great example of a mineral cofactor that an enzyme like DNA polymerase would use. Now, not all minerals act only as cofactors. Some minerals like calcium, which can act as a cofactor, is also a critically important component of bone and teeth. And it doesn't strictly act as an enzyme cofactor here. It's actually an important part of the structure itself. So what did we learn? Aren't carbon-based, and minerals are usually just cofactors in our body. So magnesium would be a great example of a mineral cofactor that an enzyme like DNA polymerase would use. Now, not all minerals act only as cofactors. Some minerals like calcium, which can act as a cofactor, is also a critically important component of bone and teeth. And it doesn't strictly act as an enzyme cofactor here. It's actually an important part of the structure itself. So what did we learn? Well, first we learned that not all enzymes are able to function alone, and some need a little help. And next we learned that this help can come from coenzymes, which usually act as carrier molecules, or cofactors, which directly assist with the catalysis that the enzyme is doing. And finally, we learned that vitamins and minerals generally refer to dietary cofactors and coenzymes.
I think the cofactors are the minerals, and then the vitamins are coenzymes. Yeah. Gotcha.
So
Little hot. Do I have to know the 6 types of enzymes? I got it, buddy. I got it. Thank you.
today we're going to talk about enzymes and all the different kinds of reactions that.
And we're almost done with this one. I don't know how long the other one's going to take. Hopefully not too long, but we'll see. Genetic mutations. There's the Huffing Crab Cycle is here. Oh, it's on week 9. All right, let's take our 10-minute. Well, that's it, eh? Sure. Yeah, I think that's fine. We'll finish this one today. That might be all we have time for, but I think maybe tomorrow I'll be a little bit more focused. It'd be nice if I could finish enzyme kinetics as well. They most likely tie into each other. Now let's finish both these today before we start the next ones tomorrow. 1, 2, 3. 1, 2, 3. 1, 2. 1, 2, 3. Thursday. 1, 2, 3. Friday. Wait, did I do it right? 1, 2, 3. Thursday. 1, 2, 3. Friday. 1, 2. Saturday. Sunday timing charts and these. We kind of barely made it, but that's fine. That's fine. I'm actually just only gonna follow this, so that's okay. Anybody say anything? Yeah, with this, I'm
Better sit down. Enough. Where am I at right now?
But before we do
What the heck?
that, let's review the idea that enzymes make biochemical reactions go faster. And if you look at a reaction coordinate diagram, you notice that enzymes speed up reactions by lowering their activation energy. Now, enzymes are generally named for their reactions, which is convenient because it makes it a lot easier to remember what an enzyme does if someone gives you its name. And a great example of this is that one of the enzymes involved in DNA replication is called DNA polymerase, which is named as such because it acts on DNA and specifically makes polymers of DNA. Now, the suffix ase is usually just one that you find at the end of most enzyme names. Now, another great example is that the enzyme that catalyzes the first step of glycolysis, which you may remember is the reaction between glucose and ATP to form glucose 6-phosphate and ADP,
Should I memorize these? That's probably part of the next part. And kinetics.
is called hexokinase. And hexo refers to the number 6, which is a reference to glucose being a 6th carbon sugar. And kinase is a term referring to enzymes that add phosphate functional groups to different substrates. So overall, hexokinase ATP is named as such because it acts on DNA and specifically makes polymers of DNA. Now, the suffix ase is usually just one that you find at the end of most enzyme names. Now, another great example is that the enzyme that catalyzes the first step of glycolysis, which you may remember is the reaction between glucose and ATP to form glucose 6-phosphate and ADP, is called hexokinase. And hexo refers to the number 6, which is a reference to glucose being a 6th carbon sugar. And kinase is a term referring to enzymes that add phosphate functional groups to different substrates. So overall, hexokinase adds phosphates to 6 carbon sugars like glucose. Now, generally, every enzyme has a very specific name that gives insight into the specific reaction that that enzyme can catalyze. So we can actually divide most enzymes into 6 different categories based off the kinds of reactions that they catalyze. Now, our first group is the transferase group. And the basic reaction that transferases catalyze are ones where you move some functional group X from molecule B to molecule A. And a great example of one of these reactions occurs during protein translation, where amino acids bound to tRNA molecules are transferred over to the growing polypeptide chain. So in this case, A refers to our amino acid chain, B refers to our tRNA, and X refers to this lysine residue, which is being transferred from B to A. And this reaction in particular is catalyzed by an enzyme called peptidyl transferase, which is an appropriate name since it is a transferase involved in making peptides. Next, we have the ligase group, which catalyzes reactions between 2 molecules, A and B, that are combining to form a complex between the two, or AB. And an example of a reaction using a ligase that you might be familiar with occurs during DNA replication, where 2 strands of DNA are being joined together. So in this reaction, A and B represent the 2 separated DNA polymers, which are being joined to form a single strand. And this reaction in particular is catalyzed by an enzyme called DNA ligase, which is named since it's a ligase that works on DNA strands. Now, our third group is the oxidoreductase group, which is a little different from the others since it actually includes 2 different types of reactions. And these reactions involve transferring electrons from either molecule B to molecule A, or from molecule A to molecule B. Now, we say that an oxidase is directly involved in oxidizing or taking electrons away from a molecule, while a reductase is involved in reducing or giving electrons to a molecule. And we call these enzymes oxidoreductases together because they can usually catalyze both the forward and reverse reactions, which is why I've used equilibrium arrows here instead of just a normal single-headed arrow. Now, a great example of an oxidation-reduction reaction occurs during lactic acid fermentation, where electrons are either passed from NADH to pyruvate or from lactic acid to NAD. Now, this reaction is catalyzed by an enzyme called lactate dehydrogenase. Remember that the word dehydrogenase refers to the removal of a hydride functional group. And that's the same as saying the removal of electrons, since hydrides are basically just hydrogen atoms with 2 electrons on them instead of just 1. Now, this enzyme is given its name since it's able to remove a hydride, or remove electrons, from
Hydride?
a molecule of lactic acid. Next, we have the isomerase group. And enzymes in this group are typically involved in reactions where a molecule, like molecule A, is being converted to one of its isomers. And an example of this type of a reaction is the conversion of glucose 6-phosphate to fructose 6-phosphate, which is one of the steps of glycolysis that you may remember. Now, this reaction is catalyzed by an enzyme called phosphoglucose isomerase, which is appropriately named since it creates isomers of glucose molecules that are phosphorylated. Now, our next category is the hydrolase category. And hydrolases use water to cleave a molecule like molecule A into 2 other molecules, B and C. And a great example of one of these reactions is the hydrolysis reaction that can occur to peptide bonds. And if we have this lysine-alanine dipeptide here, it could be reacted with water to form 2 individual amino acids that are no longer bound. And this particular hydrolysis reaction can be catalyzed by a class of enzymes that we call serine hydrolases, which some people call serine proteases. And they are named this way because they are hydrolases that use a serine residue as the key catalytic amino acid that is responsible for breaking the peptide bond. Now, our last category is a little more complicated than the others, and it's the lyase group. Now, lyases catalyze the dissociation of a molecule like molecule A into molecule B and C without using water like hydrolases would, and without using oxidation or reduction like an oxidative reductase would. And one example of a reaction catalyzed by a lyase is the cleavage of argininosuccinate into arginine and succinate. And this reaction takes place during the urea cycle, which you also might be familiar with. Now, this specific reaction is catalyzed by an enzyme called argininosuccinate lyase, which is appropriately named because it is a lyase that catalyzes the breakdown of an argininosuccinate molecule. Now, it's important to recognize that since lyases don't use water or oxidation to break a bond, they need to generate either a double bond between 2 atoms or a ring structure in a molecule in order to work. So what did we learn? Well, first we learned that enzymes are sometimes named for their reactions. And next we learned about the 6 different types of enzymes. We have transferases, which transfer functional groups from one molecule to another, ligases, which ligate or join 2 molecules together, oxidoreductases, which move electrons between molecules, isomerases, which convert a molecule from one isomer to another, hydrolases, which break bonds using water, and lyases, which break bonds without using water and without using oxidation. So today we're going to talk about the effects of the environment on enzymes and how a changing environment can affect an enzyme's ability to catalyze a reaction. But first, let's review the idea that enzymes make reactions go faster. And looking at a reaction coordinate diagram, you'd notice that enzymes speed things up by lowering a reaction's activation energy. Now, it's important to recognize that enzymes work best in specific environments. And when I say environment, I can be really referring to many different aspects of an enzyme's surroundings, but right now we're really only going to be focusing on pH and temperature values. So let's take another look at this by imagining that we have this person over here, and he's hungry, so he's eating some food. Now, there are a bunch of different digestive enzymes in this guy's body that are going to help him break down all the food he's eating into tiny usable parts. So first, the food will be in his mouth, and one of the enzymes found inside a human's mouth is called alpha amylase, which is responsible for breaking down complex carbohydrates like starches into small, simple carbohydrates like individual sugars. And alpha amylase is able to work well in your mouth since it functions best at a pH of around 7, which is about the same pH as a human's mouth. Now, moving along, the food that our guy ate is going to go all the way down to his stomach, where a whole different group of enzymes will start breaking down the food. Now, one enzyme that humans have in their stomachs is called pepsin, which breaks down big proteins into smaller peptides. Now, pepsin will be most active at a pH of around 2, which is also the pH of your stomach, which is so low because of all the stomach acid that you'd find there. Now, in terms of temperature, both of these enzymes typically work at a temperature of around 37 degrees, which is the same as body temperature. But you can see that these two different enzymes are functioning at different environmental conditions. So what would happen if we took an enzyme and moved it to work at a temperature of around 37 degrees, which is the same as body temperature? But you can see that these two different enzymes are functioning at different environmental conditions. So what would happen if we took an enzyme and moved it into a different environment? Well, let's first look at the effects of changing the pH of an enzyme's environment and jump right in with an example. So remember that DNA is a very negatively charged molecule because of all the negatively charged phosphate groups that you'd find on DNA. And in order for the enzyme DNA polymerase to help out with DNA replication, it binds a magnesium ion cofactor, which it uses to stabilize all the negative charge on DNA. Now, under normal pH conditions, the DNA polymerase will hold on to that magnesium ion through an electrostatic interaction between the magnesium and one of its aspartate residues, which would be deprotonated and thus negatively charged on DNA. Now, under normal pH conditions, the DNA polymerase will hold on to that magnesium ion through an electrostatic interaction between the magnesium and one of its aspartate residues, which would be deprotonated and thus negatively charged at neutral pH values. Now, if we are to take DNA polymerase and put it into an environment with a reduced pH, then that aspartate residue will become protonated since the pH has dropped so much. And in its protonated form, aspartate no longer has a negative charge and can't hold on to that magnesium ion anymore. And overall, this means that DNA polymerase won't be able to do its job properly in a low pH environment. And keeping this enzyme at an appropriate pH is essential to its normal function. So now let's take a look at the effects of temperature changes on enzyme function. So remember that proteins need to fold into their secondary, tertiary, and possibly quaternary structures in order to be in their functional form. And significant changes to a protein's temperature can disrupt a protein's folded geometry and cause it to lose its functionality. If we have our same person from before who's really hungry and really wants to eat, but now this person gets sick with a fever, his temperature will rise and a bunch of the digestive enzymes in his body will get all jumbled up and won't be properly folded anymore. And this is why you might have a hard time eating and digesting food when you have a fever. And this can sometimes lead you to throwing up anything you'll eat, since all of the digestive enzymes in your body won't work anymore because of the increase in your body's temperature. And the food you eat will just sit there in your body and make you feel sick. So what did we learn? Well, first we learned that enzymes generally function only under very specific environmental conditions. And different enzymes will often function ideally in different environments from other enzymes. And next we learned that changes to an enzyme's environment, like changes to the surrounding pH or temperature, can lead to a loss of enzyme functionality.